Hi everyone and welcome back to the channel. My name is Martin Yanev, a professional software engineer and a computer science professor at Fitchburg State University. And in the next few hours I will show you how you can use Python to automate cybersecurity tasks. I will show you how to use Python for network scanning, log analysis and more. I will show you how to write professional Python scripts to detect vulnerabilities, automate incident response, and integrate security tools and APIs. I am confident that by the end of this course, you will be able to create by yourself custom Python-based solutions for cybersecurity. I will link the full code for this video in the description. You can find it in our GitHub repository. Make sure you like this video so I stay motivated to create more free videos like this one. Please also make sure to subscribe my channel to follow up with the latest content. And now let's jump straight to the course.
In today's rapidly evolving cybersecurity landscape, the need for effective security measures has never been more apparent. Traditional manual methods to ensure security often fall short, especially when security teams are bombarded with thousands of alerts and logs every day. As such, the concept of security automation has emerged as a crucial solution. It allows organizations to automate the repetitive and mundane tasks that previously demanded extensive human resources, improving both the speed and accuracy of security responses. Let's dive into the world of security automation and see how Python can make a significant difference. Now let's implement a simple script to monitor log files efficiently. The function monitorLogs takes a log file path as an argument and opens it for reading. By using file seek02, the script immediately jumps to the end of the file, ensuring it starts monitoring any new entries rather than processing old data. Within an infinite loop, it reads new lines as they are added. If no new line is detected, the script sleeps briefly before checking again, which reduces unnecessary CPU usage. When a new line does appear, the script checks for the presence of keywords error or warning. If a line contains either of these terms, it indicates a potentially suspicious log entry, and the script then prints that line to the console, alerting the user immediately. This method shifts the burden of manual log analysis to an automated process, enabling security teams to respond swiftly to potential threats. Finally, the main block sets the log file path, demonstrating how to call the monitorLogs function effectively, ensuring the script is ready for immediate real-time log monitoring. Now let's see how we can implement automation for detecting unauthorized access attempts. The code begins by importing the necessary library, requests, which allows us to interact with web APIs. The checkFailedLoginAttempts function fetches login attempts from a specified API URL. It checks if the response is successful and retrieves the list of login attempts in JSON format. Within this function, we iterate through each attempt to identify any that have a status labeled as failed. For each failed attempt, we invoke the handleFailedLogin function. This function is responsible for handling the detected unsuccessful login, where it prints out the IP address from which the failed attempt originated, and subsequently calls the blockIP function to mitigate potential threats by blocking that specific IP address. The blockIP function takes an IP address as an argument, and prints a message indicating that the IP address is being blocked. In a real-world scenario, this is where we would add the logic to effectively block the IP, enhancing our automated response to security incidents. Finally, the script is set to execute the checkFailedLoginAttempts function when run as the main program, providing a practical way to automatically monitor login attempts in real time. Now let's implement the following function that automates network vulnerability scanning using the Nmap library in Python. The core of this script is the scanNetwork function, which takes a target network range as input. Within this function, we instantiate a port scanner object from the Nmap library, which allows us to conduct network scans. The scanning process begins by calling the scan method on the port scanner instance, specifying the target and the scan arguments, in this case, using a stealth SYN scan indicated by the SS argument. Once the scan is complete, we can extract and iterate through the hosts detected on the network using the allHosts method. For each host, the script prints out the host address, followed by another loop that examines each protocol associated with that host. The ports for these protocols are accessed, and the state of each pot, whether it's open, closed, or filtered, is then displayed. This structured output not only simplifies understanding the network's security posture, but also enhances the ability of cybersecurity teams to respond promptly to any vulnerabilities identified during the scan. Finally, the script includes a main guard to specify the network range to be scanned, ensuring streamlined execution. Now let's implement a logging mechanism for our automated actions. This is crucial to maintain an audit trail and ensure all operations are monitored for compliance. We begin by importing the logging module, which allows us to record events that occur while our code is executed. Next, we configure the logging settings, specifying that all logs should be stored in a file named automation log.txt with a logging level of info. This means that all messages at this level or higher will be captured. Now, let's create a function called logAction that takes an action as an argument. When this function is called, it logs the action using the loggingInfo method, which records the action with a timestamp in the log file. Next, we define another function, blockIP, which takes an IP address as an argument. Within this function, we call logAction to log that we are blocking this specific IP address, ensuring clarity in our logs. The next steps would involve adding the logic to actually block the IP, which would follow this logging implementation, emphasizing the importance of keeping track of automated actions for enhancing security and compliance. Another common challenge in security automation is managing false positives. Automated detection systems may incorrectly flag benign activities as threats, which can lead to unnecessary investigations and wasted resources. By integrating machine learning techniques, we can refine our detection algorithms to improve accuracy. The variety of libraries available in Python, such as scikit-learn, makes it easier to apply these techniques in a practical manner. Security automation represents a significant evolution in how organizations approach threat detection and response. As cyber threats continue to grow in sophistication, relying on manual methods alone is simply not an option. Automation not only enhances efficiency and accuracy, but also enables security teams to focus on higher-level strategic tasks, leaving repetitive and time-consuming processes to machines. So as we look toward the future, the message is clear. Embrace security automation with open arms. Leverage Python's incredible capabilities to transform the way your organization approaches cybersecurity, ensuring you remain one step ahead of potential threats in this dynamic landscape. To sum it all up, security automation is not just a luxury, it's a necessity in today's cybersecurity realm. It enables rapid detection, effective response, and continuous monitoring of threats, allowing organizations to maintain operational efficacy while securing their digital infrastructures. Using Python for automation enhances these processes, equipping security teams with tools that scale and adapt to ongoing challenges, all while guarding the integrity and availability of the systems they protect. With that, let's get out there and automate. The cybersecurity world is waiting and Python has your back. In this lesson, we'll dive deep into the benefits of security automation and how it revolutionizes the way organizations handle cybersecurity. So far, we learned that in the rapidly changing cybersecurity landscape, security automation has become essential for effectively managing threats and operational efficiency. Automation leverages technology to speed up tasks such as log analysis and incident response, allowing organizations to respond to threats more quickly and accurately. Python plays a key role in this automation, providing tools for real-time monitoring and incident management while reducing the burden on security teams. Ultimately, embracing security automation enables organizations to maintain a stronger defense against evolving cyber threats. Now, we will cover the specific benefits of security automation and how it enhances operational efficiency and effectiveness. Security automation addresses these challenges by leveraging technology to automate routine tasks and workflows, enabling organizations to reduce manual efforts, mitigate risks, and improve response times to security incidents. One of the most significant benefits of automation is the increased speed at which security operations can occur. For instance, consider an organization dealing with hundreds of security alerts daily. Manual analysis of each alert can take an enormous amount of time and potentially lead to human error. Automation allows us to implement systems that prioritize alerts based on severity and relevance, letting security teams focus on critical issues that require immediate attention. Now let's implement a basic alert prioritization system using Python. Here, we define an alert class that encapsulates the properties of an alert, specifically its message and severity level. Upon creating instances of this class, we can initiate a collection of alerts, each with varying severity levels that represent their importance. Next, we introduce the filter_alerts function, which takes a list of alerts as input and returns them sorted in descending order based on their severity. This sorting is crucial for ensuring that the most critical alerts are prioritized for attention. The sorting employs a lambda function as the key, making our code succinct and efficient. Finally, in the main execution block, we create a sample list of alert instances and apply our filtering function. The prioritized alerts are then printed to the console, showcasing both their severity and associated message. This implementation highlights how automation can streamline alert management, providing security teams with a clear view of which issues require immediate action, thereby enhancing their operational efficiency. Now let's see how we can automate the incident response process using Python. The analyze logs function is designed to iterate through a list of system logs and identify any unauthorized access attempts. In this function, we check each log entry for the specific text unauthorized access. If this condition is met, it triggers the respond to incident function, which handles the situation by printing a message that includes the details of the log. This simple structure effectively demonstrates how automation can minimize response times during critical security incidents. In the main execution block, we define a sample list of system logs that includes various log messages. The analyze logs function is then called with this list, allowing it to analyze the logs and respond appropriately if unauthorized access is detected. By employing this automated approach, organizations can swiftly manage security incidents, ensuring that potential threats are addressed promptly and efficiently without the need for constant human oversight. This highlights the importance of accuracy and speed in security operations, which are fundamental benefits of implementing automation in cybersecurity practices. Now let's see how we can visualize security data to enhance our understanding of threat types and their associated incidents. We'll utilize the matplotlib library, which is a powerful tool for creating static, animated, and interactive visualizations in Python. In this code, we start by defining two lists, threat types and threat counts. The threat types list includes categories such as malware, phishing, unauthorized access, and insider threat, representing different types of security threats. Correspondingly, the threat counts list holds the incident counts for each threat type, allowing us to understand how frequently each type occurs. Next, we implement a function called visualize threats, which takes these lists as arguments. Inside this function, we create a bar chart using plt bar where the threat types are on the x-axis and the number of incidents is on the y-axis. We enhance the chart's readability by adding labels for the x and y axes and a title that summarizes what the chart represents. Finally, plt show is called to render the chart. By automating this visualization process, organizations can quickly grasp their threat landscape, enabling more informed decisions on security priorities and resource allocation. Now let's implement the following code to automate the process of scanning for open parts on a specified target using the nmap library. This script begins by importing the necessary nmap module, which provides a Python interface to the powerful nmap network scanning tool. The scanParts function takes a target IP address as its parameter. Within this function, we create an instance of nmap part scanner to initiate the scanning process. By calling the scan method, we specify the target and use the ss argument, which instructs nmap to perform a TCP/SYN scan designed for stealth and efficiency. After the scan is conducted, we iterate through all detected hosts using nm all hosts. For each host, the function prints its address, providing context for the scanning operation. Then, by accessing the protocols associated with each host, we can enumerate the open parts. As we loop through each protocol, we check for open pots and print their status, indicating whether they are open or closed. This automation not only streamlines the process of vulnerability assessment, but also enables security teams to regularly monitor their network environment without manual effort, significantly increasing operational efficiency. Now let's implement the following logging functionality to enhance accountability in our security automation practices. First, we configure the logging module to create a log file called Security Automation Log, TXT, where all relevant actions will be recorded. This setup ensures that every action is not only documented but also set at an information level, making it easy to capture important events without cluttering the logs with unnecessary details. Next, we define a function called logAction that takes an action as its parameter and logs it into our file. This will be crucial for tracking changes made during security protocols. Then we implement another function, changeSecurityPolicy, which will invoke the logging function whenever a security policy is altered. It logs the specific policy change and also provides immediate feedback by printing the updated policy to the console. Finally, in our main block, we simulate the change of a security policy by passing a new policy that requires multi-factor authentication for all users. This cohesive approach not only strengthens accountability through logging, but also aligns with compliance standards, ensuring that each significant action is traceable and auditable in the context of security automation. Next, we will implement a simple filtering mechanism to handle alerts and reduce the noise caused by false positives in our security system. We begin by defining a function, isSuspicious, which takes an alert as input and analyzes its content. The filtering logic here is straightforward. It checks whether the word alert appears in the alert message, converted to lowercase to ensure the comparison is case-insensitive. This simplistic approach highlights how we can quickly establish criteria to identify suspicious activities based on known patterns. After defining the filtering function, we move into the main execution block where we have a list of alerts that simulate various security notifications. This list includes both benign activities and potential threats. We then apply our filtering function to this list, creating a new list called Filtered Alerts, which comprises only the alerts deemed suspicious based on our initial criteria. Finally, we print out these filtered alerts. This code serves as an excellent foundation for refining our alert management process, enabling security personnel to focus on genuine threats and improving operational efficiency in addressing security incidents. In conclusion, the benefits of security automation are manifold. Increased speed, accuracy, visibility, operational efficiency, accountability, and improved threat management are just a few of the significant advantages. By integrating automation into cybersecurity practices, organizations not only strengthen their defenses, but also enable their teams to work more strategically and effectively. As we have explored in this lesson, Python serves as a powerful ally in the realm of security automation. With its vast libraries and straightforward syntax, security teams can rapidly develop and implement solutions that not only meet current demands but can also scale with future challenges. Embracing security automation is no longer just an option. It's imperative for maintaining a proactive and responsive cybersecurity posture. So, equip yourselves with these tools and let's move forward to create a more secure digital world together. Implementing security automation is crucial for enhancing organizational security. However, this integration can introduce challenges that require thorough planning and execution. In this video tutorial, we will explore how to effectively implement security automation in an organization's security operations, leveraging Python and best practices to ensure a smooth transition. So far, we covered how security automation plays a vital role in enhancing cybersecurity by improving threat management, speeding up responses, and increasing accuracy. It enables organizations to reduce manual workload and human error while providing enhanced visibility into security operations. Now, we will discuss the steps and strategies involved in implementing security automation to optimize your cybersecurity efforts. When planning for security automation, it is essential to begin with a solid understanding of your current security landscape. Assess your organization's existing security measures, identify potential areas for improvement, and determine which repetitive tasks can be automated. Examples of such tasks include log analysis, incident response, and alert management. Conducting a comprehensive security gap analysis helps outline the processes needing automation to improve efficiency and accuracy. Once you have identified suitable processes for automation, it's time to define your objectives. What do you hope to achieve through automation? Be specific. Your goals may include faster response times, reduced false positives, or streamlined compliance reporting. Clarity on your desired outcomes will guide the implementation and help you measure success later. Now let's see how we can automate the creation of tickets for security incidents using a Python script. We begin by importing the requests library, which enables us to make HTTP requests to an API. The core of our script is a function called createTicket, which takes incident details as an argument. Within this function, we define the API endpoint URL for the ticketing system and specify the necessary headers, including an authorization token and content type. Next, we prepare the data to be sent to the API, which consists of the incident's title and description. By utilizing the requestsPost method, we send this data in JSON format to create a new ticket. After submitting the request, the script checks the response status code to determine if the ticket was successfully created. A status code of 201 indicates success, prompting the script to print a confirmation message. Conversely, if the request fails, it outputs an error message along with the response content. Finally, in the main program block, we create a sample incident and call the createTicket function to automate the ticket creation process efficiently. Now let's implement a Python script to prioritize security alerts based on their severity levels. In this code, we define an alert class that allows us to create alert objects, each containing a message and a severity attribute. The severity indicates the level of threat posed by the alert, with higher numbers representing more critical issues. Next, we write a function called filterAlerts that accepts a list of alert objects as its parameter. This function uses Python's built-in sorted method to arrange the alerts by severity in descending order. By employing a lambda function as the key, we instruct the sort operation to refer to the severity attribute of each alert. In the main block of the script, we create a list of sample alerts, each with varying severity levels. Once we call the filterAlerts function with this list, it returns a new list of alerts sorted from the most critical to the least severe. Finally, we iterate through the prioritized alerts and print the severity levels along with their messages. This approach empowers security teams to tackle the most pressing threats efficiently, enhancing their incident response capabilities. Now let's see how we can automate incident response by analyzing system logs for unauthorized access attempts. The first function, analyzeLogs, takes a list of logs as input and iterates through each log entry. Within this loop, it checks whether the phrase unauthorized access is present. If it finds a match, it calls the respondToIncident function, triggering an automated response to the identified incident. The respondToIncident function takes the specific log that triggered the alert as an argument and prints a message indicating that the incident is being investigated. This approach allows for immediate action to be taken based on predefined conditions defined in the first function. Finally, in the main block of the code, we define a sample list named systemLogs that contains different log entries, including one indicating an unauthorized access attempt. By executing analyzeLogs systemLogs, we enable the script to review the logs and respond accordingly, illustrating how this automation can significantly enhance threat management and reduce response times. This simple yet effective method underscores the importance of developing a structured incident response playbook within your security operations. Now let's see how we can implement a basic filtering mechanism using Python to identify suspicious alerts. The core of this script revolves around the isSuspicious function, which checks whether a given alert message contains specific keywords that may indicate a potential threat. This function uses the LOA method to ensure the check is case insensitive, making the filtering more robust. Next, we have a list of alerts representing different system activities. These alerts vary from unauthorized access attempts to normal user logins. By employing a list comprehension, we can efficiently filter through these alerts, leveraging our isSuspicious function to determine which alerts should be considered suspicious. Finally, the script outputs the filtered list of alerts, allowing security teams to focus their attention on potentially serious issues, thereby enhancing the effectiveness of their automated systems. This approach serves as a foundational step in reducing false positives and prioritizing real threats in cybersecurity operations. Now let's implement a robust logging mechanism to record our security-related actions. This code begins by importing Python's built-in logging module, which provides an efficient way to log events in your application. We configure the logging system to write messages to a file named Security Automation Log, TXT, with an information level, meaning it will log informational messages and above, which is ideal for tracking important actions. Next, we define a helper function called logAction, which takes an action description as an argument and logs it with an info level. This is useful for creating an audit trail of actions performed by our automated systems. Following that, we introduce a function called change security policy, which not only calls logAction to record when a security policy is changed, but also prints a message to the console to confirm the action taken. In the main execution block, we specify a new security policy and invoke the change security policy function, demonstrating how easily we can log the change while ensuring traceability. This approach reinforces accountability and helps maintain compliance with security standards by documenting crucial actions within our automated systems. Training and awareness are equally important when implementing security automation. Employees need to understand how automation impacts their workflows and what responsibilities they carry. Regular training can help familiarize everyone with new automated systems, ensuring smoother transitions and minimal disruption. Moreover, consider encouraging feedback to continuously improve automated processes. Frontline employees who deal with alerts and incidents can provide invaluable insights into how well the automation functions and where it can be improved. Make it a routine practice for employees to share their experiences with the automated systems, allowing for ongoing optimization. Now let's implement a key step in our security automation context, visualizing incident response times before and after automation. We'll use the matplotlib library to create a clear comparison that highlights the impact of our automation initiatives. The code begins by importing the necessary pyplot module from matplotlib, which is essential for creating plots. We then define two lists, prior response times and post-response times. These lists contain sample data representing the average incident response times measured in seconds before and after automation implementation. Next, we make use of the pltplot function to create line plots for both datasets. The first plot showcases prior response times with circular markers, while the second plot illustrates post-automation response times with cross markers. This distinct coloring and shape help differentiate between the two timelines. To effectively communicate the information, we set a title for the plot, label the x-axis with incident number, and the y-axis with response time, seconds. Finally, we add a legend to clarify which line corresponds to which dataset, followed by displaying the completed plot using pltshow. This visual representation helps teams evaluate the effectiveness of their automation efforts and make data-driven decisions for continuous improvement. To wrap up, implementing security automation is a multifaceted process that requires careful planning, integration, and ongoing evaluation. By identifying tasks ripe for automation, setting specific objectives, and utilizing Python tools and libraries, organizations can drastically enhance their cybersecurity posture. Engagement and training among employees will further bolster the effectiveness of these systems, ensuring a proactive approach to managing cyber threats. Remember, security automation isn't just about technology. It's about creating an agile ecosystem that can adapt to change and tackle the dynamic landscape of cybersecurity challenges. With the right strategies in place, automation will not only help streamline security operations, it will empower your teams to be more effective in their roles, allowing them to focus on being strategic actors in the realm of cybersecurity rather than merely reactive troubleshooters. So let's embrace security automation together and pave the way for a more secure digital future. In today's lesson, we're diving into advanced security automation techniques to enhance our cybersecurity arsenal using Python. We'll explore network monitoring and intrusion detection systems that allow our organizations to detect threats before they escalate. So far, we've learned about the importance of implementing security automation to improve organizational security by enhancing threat management and reducing human error. We also discussed assessing the current security landscape, defining clear objectives, and integrating existing security tools. Now, we will cover advanced automation techniques to bolster our defensive strategies in dynamic environments. Now let's see how we can implement a basic packet capturing script using the Scapy library. In this code, we first import the sniff function from Scapy all, which is essential for capturing network packets. We then define the packet callback function responsible for processing each packet captured. Inside this function, we use print to display a summary of each packet, giving us a quick insight into its content. Moving on, we set up our main execution block, where we initiate packet capturing. We print a message to inform users that packet capture has started and provide guidance on how to stop the process. When we call the sniff function, we specify a few parameters. PRN equals packet callback indicates that the packet callback function should handle packets as they are captured, while count equals 10 limits the capture to only 10 packets. This straightforward setup provides a foundation for observing network activity in real time, which can be built upon for more advanced monitoring methods in our cybersecurity toolkit. Now let's see how we can implement packet filtering to focus our monitoring on specific types of traffic. In this code snippet, we modify the sniff function to include a filter that captures only packets related to HTTP and DNS. This is achieved by specifying the filter parameter as TCP port 80 or UDP port 53, which targets TCP traffic on port 80, commonly used for HTTP, and UDP traffic on port 53, used for DNS queries. By incorporating these filters, we refine our packet capture to only the most relevant data, which is critical for network analysis and security monitoring. The callback function, packet callback, remains the same, processing each captured packet to provide meaningful output. Furthermore, we adjust the count to 50 packets, allowing us to gather a broader sample while still keeping the monitoring focused and efficient. This enhanced approach not only speeds up the analysis process by eliminating unnecessary data, but also allows us to quickly identify trends and anomalies specific to web traffic and DNS communications, which are often targets for security attacks. Now let's see how we can implement a basic rule-based system to detect communication with known command and control C and C servers. In this section, we define a list of bad IPs containing IP addresses that are flagged as malicious. Our enhanced packet callback function is designed to analyze each captured packet, specifically checking if it contains IP data. If the packet's destination IP matches any IP in our bad IPs list, an alert is triggered with a clear message indicating the specific packet involved, helping us identify potential threats in real time. Conversely, if the packet does not match any known bad IP address, a simple notification is printed to indicate that the packet was captured without any issues. This functionality not only allows us to maintain vigilance over suspicious activity, but also ensures we continue to collect broader network data without interruptions. By integrating this rule-checking mechanism into our packet capture script, we enhance our overall security posture and responsiveness to potential cyber threats, making our network monitoring efforts more robust and proactive in identifying malicious communications. Next, we will implement a lightweight intrusion detection system, IDS, that can track connection attempts from different source IPs. To achieve this, we utilize a default dict from the collections module to keep account of connection attempts for each IP address without needing to initialize keys. The packet callback function processes incoming packets, checking if they contain IP data. If the packet does, it extracts the source IP address and increments its count in our connection attempts dictionary. Importantly, we've set a threshold of 5 connection attempts, If any source IP surpasses this limit, an alert is generated, notifying us of the excessive attempts. After alerting, the count for that specific IP is reset, preventing repeated notifications for the same offender. This logic helps in identifying potential brute force attacks or scanning activities aimed at compromising our systems. Finally, within a loop in the main section, we initiate the sniff function without a limit on the number of captured packets, allowing continuous monitoring of network traffic. This system effectively enhances our security posture by providing real-time alerts and facilitating proactive measures against possible threats. Next, we will implement a crucial feature for enriching our network monitoring by adding geolocation data to captured packets. This enhancement makes it possible to understand the origins of suspicious IP addresses more clearly, providing context that can help assess potential threats. We begin by importing the requests library, which allows us to make HTTP requests to an external API, in this case the Apinfo EO service. We define the getGeolocation function that takes an IP address as input and queries the API. The function extracts country and city information from the returned JSON data, defaulting to unknown if the data is not available. In the packet callback function, we check if the packet contains IP information. If it does, we extract the source IP address and pass it to our getGeolocation function. The return location data, country and city, are then printed alongside the source IP, providing immediate contextual insight for every captured packet. This addition allows network analysts to quickly discern whether a source IP might be associated with malicious activity based on its geographical origin. By combining packet capturing with geolocation, we enhance our monitoring capabilities significantly. Next, we will write the following code to establish automated remediation by blocking suspicious IP addresses based on connection attempts. The block IP function is designed to execute a system command that adds the specified IP address to the iptables rules, effectively preventing any further traffic from that source. This is crucial for isolating potentially harmful devices. The packet callback function analyzes incoming packets and keeps track of connection attempts from each source IP address, stored in a dictionary named connection attempts. When an IP address exceeds a threshold of 5 connection attempts, the block IP function is invoked, triggering the blocking action, and the count for that IP is reset to ensure effective monitoring. By integrating this automated response mechanism in our existing network monitoring system, where packets are continuously sniffed, we can react swiftly to potential threats as they arise. However, it's essential to emphasize the importance of threshold management to avoid inadvertently blocking legitimate users. This powerful approach empowers organizations to enhance their cybersecurity defenses decisively while minimizing manual intervention. Now let's implement a logging mechanism that captures alerts generated during packet monitoring. In this code, we define a function called logalert that takes the source IP, city, and country as parameters. This function opens a CSV file in append mode, allowing us to record each alert without overwriting previous entries. Using the CSV writer, we log critical information including the timestamp, source IP, and its corresponding geolocation data. Next, we modify the packet callback function to include our logging feature. Whenever a packet containing IP information is detected, we extract the source IP and retrieve its geolocation data using the getGeolocation function. This data is then passed to the logalert function to log it into our CSV file, enabling us to maintain a concentrated record of alerts. Additionally, we print the packet information, displaying the source IP along with its geographical context. This approach enhances our monitoring system by ensuring that vital alert information is stored for further analysis or trend identification, which is essential in developing strategic security responses over time. In summary, we've taken a thrilling dive into advanced security automation techniques, exploring network monitoring, intrusion detection, automated responses, and reporting capabilities. These techniques equip us with the tools to detect threats, understand the context around them, and respond swiftly, minimizing risk. Remember, the cybersecurity landscape is ever-evolving, and keeping your defenses up to date will demand continuous learning and adaptation. The integration of Python for automating these security measures not only enhances efficiency but empowers organizations to act proactively against potential threats. Thank you for joining me today as we ventured through these advanced techniques in security automation. By implementing what you've learned here today, you're well on your way to becoming a formidable defender in the ever-competitive field of cybersecurity. Before diving into the world of security automation with Python, it's crucial to establish a well-configured development environment. This is the foundation that allows you to efficiently write, test, and deploy Python scripts for various security tasks. Today, we will discuss how to set up your development environment, covering everything from installing Python to managing dependencies and choosing the right tools. So far, we learned about advanced security automation techniques in cybersecurity using Python, focusing on network monitoring and intrusion detection systems. We covered the importance of implementing security automation to improve threat management and reduce human error, as well as how to filter specific network packets for analysis. Additionally, we explored concepts of data enrichment and automated remediation, enabling rapid responses to identified threats. Lastly, we emphasized the significance of reporting and visualization to maintain a clear view of our security posture. Now, we will talk about setting up a tailored development environment that will empower you with the tools to harness the full potential of Python in your security automation tasks. Next, we will write the following commands to install Python on different operating systems, ensuring that you have the right setup for your security automation tasks. For macOS users, we will utilize Homebrew, a popular package manager that simplifies software installations. By executing the command brew install Python, you will quickly download and set up Python. This command is efficient and makes it easy to keep your Python installation up to date with Homebrew's package management features. On Linux, particularly for those using Ubuntu, the process is slightly different. Here we need to first update the package lists with sudo apt-get update, and then install Python by running sudo apt-get install python 3. This ensures that you are installing the latest available version of Python from your distribution's repository, which is essential for accessing the latest features and security updates. Once the installation is complete, verifying your setup is crucial. You can do this by checking the installed version of Python in your terminal using Python version or Python 3 version. These commands will confirm that the installation was successful and help you identify the version of Python you are working with, laying the groundwork for your automation projects. Next, we will explore how to manage the packages and libraries necessary for your security automation projects using Python's package manager, pip. First, to verify that pip is installed on your system, you can check its version by running a simple command. This command will confirm whether pip is available and ready for use, which is crucial for managing your project dependencies. Now let's see how we can install the essential libraries for security automation. We'll utilize pip to install requests, Scapy and Paramiko. The requests library simplifies making HTTP requests, which is vital when interacting with web applications or services. Meanwhile, Scapy is a powerful tool for packet manipulation, enabling you to capture and analyze network traffic, an essential skill in cybersecurity tasks. Lastly, Paramiko provides SSH functionalities, which are important for executing remote commands securely. As you set up your environment, it's also a good practice to document your dependencies. You can do this by creating a requirements.txt file. This file lists all the libraries you've installed, making it easy for other developers to replicate your environment. You can generate this file with a command that captures the current state of your installed packages. This step ensures your project is consistent and maintainable, especially when collaborating with others. Now let's see how we can effectively manage dependencies for our projects by creating a virtual environment. First, we will execute a command using Python's built-in venv module, which will create a self-contained directory named venv within our project folder. This isolates our project's packages and dependencies, preventing conflicts between different projects that may require different versions of the same libraries. Once the virtual environment is created, we need to activate it to start using it. If you are using Windows, the command to activate it is specific to that operating system, and you'll run the script located in the scripts folder of the venv. Alternatively, for macOS or Linux users, Activation is done via the source command that points to the bin directory within the virtual environment. After activation, your terminal prompt should change to indicate that you are now working within that environment. This allows you to install any additional packages without affecting other projects. Finally, when you finish working, you can easily deactivate the environment with a simple command, returning your terminal to its original state. This approach ensures a clean and organized development setup, essential for effective security automation tasks. Next, we will install code linters and formatters to enhance our coding practices. These tools help maintain code quality by checking for errors and ensuring that your code adheres to style guidelines. Now let's see how we can implement Flake 8, a popular linter that checks your Python code for style guide enforcement errors and complexity issues. By running the command pip install Flake 8, you install it directly into your development environment, making it easy to run and utilize. To further reinforce consistent style in your code, let's also install Black, a code formatter. By executing the command pip install Black, you ensure that your code follows a uniform style that enhances readability. What's great about using Black is that it formats your code automatically, so you can focus on writing logic without worrying about the minutiae of style. By incorporating both Flake 8 and Black, you'll have a solid foundation for producing clean, efficient, and high-quality code as you develop your security applications in Python. After installing these tools, you can run them regularly as part of your workflow to maintain coding standards. Now let's see how we can securely manage sensitive information in our Python applications using environment variables. By importing the OS module, we gain access to the operating system's functionality, which includes retrieving environment variables. We can use the OS getenv function to safely obtain our API keys without hard-coding them into our scripts. This practice not only protects our sensitive data from unauthorized access, but also helps us avoid accidental exposure when sharing our code. Next, we will implement logging to keep track of critical events in our application. By importing the logging module and configuring it with basic config, we set the logging level to info, which allows us to capture a range of messages, including informational ones. By placing a log entry, we can document significant milestones during execution, such as successful API calls or error occurrences. This approach helps us to maintain a clear operational record, making it easier to debug and track issues as they arise. Keeping consistent logs is essential, especially in security-focused applications where accountability and traceability are vital. Now let's focus on establishing version control for our project. A critical step in any software development process, particularly in security automation, is initializing a Git repository within your project folder. By executing the command git init, you are creating a new Git repository that allows you to track your project's changes over time. This not only helps in managing your code, but also plays a vital role in collaboration with others. As you continue development, this version control system enables you to create snapshots of your project through commits, which you can reference later if needed. It's essential to get into the habit of committing regularly to save your progress and push your changes to a remote repository, ensuring that you have backups and the ability to work with team members seamlessly. Additionally, don't forget to create a gitignore file to avoid pushing unnecessary files such as virtual environments or sensitive information to the repository. This practice will keep your codebase clean and secure, setting the foundation for a professional coding environment. In summary, you have learned how to set up a robust Python development environment tailored for security automation. From installing Python and setting up virtual environments to managing dependencies and employing best practices in coding and security, you now have the tools to start your automation tasks with confidence. Going forward, with a well-configured development environment, you are equipped to create scripts, automate processes, and ultimately contribute significantly to your organization's cybersecurity efforts. So, get ready to dive deeper into using Python for practical security applications. Exciting times lie ahead. To effectively manage project-specific libraries and dependencies in Python, we must understand the concept of virtual environments. Virtual environments create an isolated space where these libraries can be installed without interfering with other projects. This not only helps to avoid version conflicts, but also keeps our projects organized and streamlined. Today's lesson will capitalize on this idea as we explore how to manage dependencies effectively using virtual environments. So far, we learned about setting up a robust Python development environment for security automation, covering installations, dependency management, and the use of virtual environments. We emphasized the importance of selecting the right integrated development environment (IDE) and following coding best practices to enhance security and reduce vulnerabilities. Additionally, we discussed the significance of version control with Git to manage changes effectively. As we move forward, you'll be prepared to create and automate security scripts confidently. Now let's implement the following commands to set up our virtual environment. First, we create a new directory called My Project, which serves as the workspace for our project. This is an essential step as it helps us organize our files and keeps everything related to this specific project contained. After creating the directory, we navigate into it using the cd my project command. This sets our working context to my project, allowing us to operate within this directory. Next, we utilize Python's built-in venv module to create a virtual environment named venv. The command python mvenv accomplishes this task, establishing a new directory called venv within my project. This directory will contain a fresh installation of Python along with its necessary libraries, isolated from any global packages. By using this structured approach, we ensure that the dependencies for this project are neatly segregated and won't interfere with those of any other projects. This is the foundation for a clean development environment, enabling us to maintain organization and avoid conflicts as we proceed with our project. Now that we've set up our virtual environment, it's crucial to activate it before running any Python or pip commands. For Windows users, we'll write the command to activate the virtual environment using venv /scripts/activate. This will configure your command line to utilize the Python libraries from our isolated environment instead of the global installation, providing you with an organized workspace. For those on macOS and Linux, the activation command differs slightly, as you'll use saucevenv/bin/activate. This command accomplishes the same task, changing your command line context to indicate the active virtual environment. Once activated, the prompt will change to reflect this shift, reinforcing that you're working within this contained setup. Next, we will see how to manage dependencies effectively. After activating your environment, we'll install the requests library by typing pip install requests. This powerful library allows us to make HTTP requests seamlessly in our projects. By using pip within the activated environment, you can ensure that such installations do not interfere with other projects, maintaining clean and conflict-free development. To manage project dependencies effectively, we can generate a requirements.txt file. By using the command pip freeze requirements.txt, we create a text file that lists all the libraries currently installed in our virtual environment, along with their specific versions. This is essential for ensuring consistency across various setups, as it enables anyone involved in the project to effortlessly replicate the same environment. The pip freeze command gathers information about the installed packages and outputs it in a way that pip can easily read for reinstalling the libraries later. By redirecting this output to requirements.txt, we ensure that all necessary dependencies are documented properly. The resulting text file accurately captures the versions of the libraries, for instance specifying that the requests library is at version 2.26.0. This document acts as a shared resource, making it easier for new contributors to set up the project and ensuring that it remains functional over time, even as changes occur in the library ecosystem. Committing this file to version control enhances the onboarding process for anyone looking to replicate our project's environment. Now let's see how we can install our project's dependencies using the requirements.txt file we discussed. By running the command pip install r requirements.txt, we instruct pip to read the list of libraries and their specified versions from the requirements.txt file and install them into our currently activated virtual environment. This ensures that your project has all the necessary components to run smoothly, without causing interference with other projects or libraries installed globally. Next, we will look at updating any libraries that may require a newer version. Libraries often receive updates, some of which may change functionality or address vulnerabilities. To upgrade a specific installed package, we can execute pip install upgrade requests, where requests is the name of the library we wish to update. By running this command, pip fetches the latest version available and replaces the currently installed version in our active environment, ensuring that we stay up to date with improvements and security patches. This practice is critical in maintaining the health and functionality of our projects as technology evolves. Now let's see how we can manage our project dependencies efficiently using a tool called pipeinv. First, we need to install pipeinv globally, which combines the functionality of pip and virtualenv into a single command, making dependency and environment management quite straightforward. By using pip install pipeinv, we can easily set it up on our system. Once pipeinv is installed, we can move to our project directory and run the command pipeinv install requests. This powerful command not only creates a new virtual environment tailored for our project, but also installs the requests library into it. What's particularly useful about this is that it will automatically generate two crucial files, pipfile and pipfile-lock. The pipfile serves as a simple and clear way to manage our dependencies, while the pipfile-lock ensures that we record the exact versions used, enabling reproducibility of our environment. Next, to work within this virtual environment, we can use the command pipeinv shell. This will activate the shell tied to the project's environment, allowing us to execute scripts or install additional libraries without affecting our global setup, thus maintaining a clean and organized workspace. Now let's see how we can properly exit our virtual environment after working on our project. Deactivating the virtual environment is crucial to ensure that you're not unintentionally using the dependencies or settings specific to that environment in future sessions. By typing deactivate, you signal to the command line that you want to exit the isolated environment, and you'll notice that your command prompt returns to its normal state. This is a visual indicator that you're now operating within the global Python environment again. Properly deactivating your virtual environment helps avoid confusion, particularly when you return to a project after some time or switch between multiple projects. It's a small step, but it can save you from a cascade of problems later on. Additionally, remember that once you're finished with a project and no longer need the virtual environment, you can clean up by deleting the venv folder in your project directory. Just be certain you no longer need it before doing so, as this action cannot be undone. While we've discussed a lot of the technical implementation, let's touch on some best practices when working with virtual environments. Always create a new virtual environment for each project. This isolates dependencies, ensuring your projects remain clean and organized. Another good practice is to keep your requirements txt or pipfile updated. After adding or removing libraries, make sure to regenerate these files accordingly. Doing so will save time and trouble later on, particularly in larger projects. Lastly, document your environment setup process in your project's README file. Include instructions on how to create and activate the virtual environment and how to install the necessary dependencies. This way, anyone aiming to work on the project will have a smooth onboarding experience. In conclusion, mastering virtual environments is a necessary skill for any Python developer, particularly in the realms of automation and security scripting. The ability to manage dependencies effectively can save time and avoid conflicts, ensuring a seamless workflow. By following the practices discussed, you'll enhance your coding experience and minimize potential issues. As we progress, these skills will lay a solid foundation for not just managing libraries, but for writing clean, secure scripts that can be shared and used within the cybersecurity domain. So, keep coding, keep building your projects, and soon you'll be automating tasks like a pro. Choosing the right tools for development can significantly enhance your productivity and efficiency as a programmer. The tools you select can impact everything from debugging to code organization. In this lesson, we will explore how to pick the best integrated development environment for your needs, delve into different tools available for Python development, and provide helpful examples along the way. So far, we learned about the importance of virtual environments in managing project-specific libraries and dependencies in Python, which helps avoid conflicts and keeps projects organized. We explored how to create and activate virtual environments, install dependencies using pip, and generate a requirements txt file for reproducibility. Additionally, we introduced pipinv as a tool for managing dependencies and virtual environments more easily. Finally, we emphasized best practices for maintaining virtual environments and ensuring a smooth development process. Now we will talk about choosing the right tools that fit your development style and improve your productivity. When it comes to selecting an IDE, it largely depends on your personal preference and the specific features you find most helpful in your workflow. Some popular IDEs among Python developers include PyCharm, Visual Studio Code, Jupyter Notebook, and Spider. Each of these tools has its own unique advantages that cater to different kinds of projects and workflows. Let's dive deeper into these options to see what each has to offer. Now let's see how we can check the installed packages in our PyCharm environment using a simple Python script. The code begins by importing the pkg resources module, which is part of the setup tools package and provides an interface for querying and managing Python packages. Next, it retrieves a list of all installed packages in the current Python environment by accessing pkg resources working set. This collection contains information on every package installed along with its version, which is crucial for ensuring that your project has all necessary dependencies correctly set up. The code then creates a sorted list comprehension that formats each package name alongside its version in the format package == version. This allows for clear visibility regarding what is currently installed. Finally, the script iterates through this formatted list and prints each package and its version to the console. This is particularly useful for verifying that your environment is configured correctly and that you're able to manage dependencies effectively, especially when working on larger projects or collaborating with others. Now let's take a look at a simple Python script that demonstrates the fundamental structure of a Python program. This code begins with the definition of a function called greet, which takes one parameter, name. Inside the function, a formatted string is returned using an fstring, allowing for an easy insertion of the name variable into the greeting. Next, we have a conditional statement that checks if the script is being run directly. This is done by evaluating the name variable. If it equals main, it indicates that the script is the entry point of the program. Within this condition, the greet function is called with the argument world, and the result is printed to the console. This structure illustrates a key aspect of Python programming, the use of functions to encapsulate behavior and the convention of script entry points, which aids in code organization and reusability. It's a fundamental pattern you'll use frequently as you build more complex projects. Now let's implement the following code to visualize a sine wave using Python libraries. We begin by importing the necessary libraries, NumPy and Matplotlib. NumPy is a powerful numerical computing library that allows us to create and manipulate arrays efficiently, while Matplotlib is a widely used library for creating static, animated, and interactive visualizations in Python. Next, we generate a set of values for the x-axis using NumPy's linspace function, which creates an array of evenly spaced values over a specified interval, from 0 to 10 in this case. This method is useful for plotting functions because it ensures we have a smooth curve. To calculate the corresponding y values, we use the sine function, which takes the x values and computes their sign. Now let's create the plot with Matplotlib. We utilize the plot method to visualize the x and y values as a line graph. Adding a title and labels for both axes is important for clarity, providing context to the viewer. Finally, the grid enhances the readability of the chart, and the show method displays the plot. This demonstration illustrates how easily coding and visualization can be combined in Jupyter Notebook, enhancing both analysis and presentation of the results. Now let's implement the following code snippet that demonstrates how to create and display a data frame using the pandas library. First, we start by importing pandas as PD, which is a standard convention in Python for ease of use. Next, we define a simple dictionary named data that contains two keys, name and age, where name holds a list of 3 names and age contains their respective ages. Following that, we create a data frame df from the data dictionary using the pd data frame function. This function converts our dictionary into a structured table, allowing for easy manipulation and analysis of the data. Lastly, we employ the print function to display the contents of the data frame. Running this code in Spider will provide a clear view of the data in a tabular format, making it straightforward to inspect both the names and their ages. The built-in variable explorer in Spider enhances this experience further by letting you visualize the data frame's contents interactively, aiding in data analysis and exploration. Now let's implement a simple Git setup to manage version control for our Python project, which is essential for tracking changes and collaborating effectively. First, we will initialize a new Git repository in our project folder using the command git init. This command sets up a new Git directory in your project, allowing Git to track changes to your files. Next, we need to add the files we want to track by using the command git add. This command stages all the current files in your project directory, preparing them to be committed. It's important to add only the necessary files so that your repository remains organized and free of unnecessary clutter. Finally, to save your changes in the repository, we will commit these files with a descriptive message, using git commit m initial commit. This creates a snapshot of your project at this point in time, allowing you to revert back to this state if needed. This workflow establishes a robust version control foundation, enhancing your ability to manage your code effectively as the project evolves. As we wrap up our exploration of development tools, it's vital to reflect on your personal workflow and the nature of your projects. What type of projects do you typically engage with? Are they web applications, data analysis tasks, or perhaps something more complex? Aligning your choice of IDE with your specific needs will make a significant difference in your output. For those working in varied areas, including web development, data science, or machine learning, the flexibility of tools like Visual Studio Code and Jupyter Notebook may suit you best. If your focus rests heavily on large, structured projects, PyCharm provides a level of support and organization that can't be overlooked. Spider serves the niche of scientific programming exceptionally well, especially for those already engaged with the Anaconda ecosystem. In conclusion, the choice of development tools extends beyond mere personal preference. It significantly affects how effectively you can write, debug, and run your code. Exploring different IDEs, understanding their strengths and weaknesses, and aligning them with the projects you undertake sets the foundation for a smoother, more productive development experience. Whether you're just starting out or are an experienced developer, the right tools can make a world of difference in the way you approach programming tasks. Thank you for joining me in today's lesson, and happy coding as you explore the capabilities of these powerful development tools. In today's lesson, we will explore best practices for security automation, which is critical for organizations striving to create robust security infrastructures. By following these practices, organizations can integrate tools like OpenCTI into their security operations, enhancing their capability to swiftly and accurately detect, analyze, and respond to threats. So far, we learned about the importance of selecting the right development tools, which can significantly impact productivity and code organization. We explored popular integrated development environments like PyCharm, Visual Studio Code, Jupyter Notebook, and Spider, highlighting the unique features and suitability for different types of projects. We also covered best practices for managing virtual environments and integrating version control with tools like Git. Now we will dive into security automation and the best methods to implement it effectively. Security automation is the use of technology to perform repetitive security tasks without direct human intervention. The benefits of automation are clear. It reduces human error, increases efficiency, and enables security teams to focus on more complex tasks. One key aspect of security automation is the ability to continuously monitor systems for vulnerabilities. For example, utilizing tools like OpenCTI helps pull together threat intelligence so that organizations can maintain a stronger grip on incoming threats. Now let's implement the initial setup for utilizing OpenCTI with Python. We begin by creating a virtual environment, a crucial step for maintaining clean project dependencies, which isolates our setup from other projects on the system. This guarantees that any libraries we install will not interfere with other projects. Depending on your operating system, you will use different commands to activate the virtual environment. Next, we will install the requests library, which is essential for making HTTP requests to APIs. This library simplifies the process of communicating with the OpenCTI framework's REST API, enabling us to pull and interact with threat intelligence data effectively. Now let's take a look at how we can interact with the OpenCTI API by defining a function called getLatestObservables. This function takes two parameters, the API URL and an authentication token. Inside the function we set the necessary headers, including the authorization token needed to access the API. The function sends a GET request to the observables endpoint and checks the response status. If successful, it retrieves the latest threat observables as a JSON object, enabling us to analyze current threats efficiently. If the request fails, it provides feedback on the error, helping to troubleshoot issues promptly. Next, we will implement a simple automated incident response function using the Prioritization library. The function lockUserAccount is designed to simulate locking a user's account when an unauthorized access attempt is detected. When the function is called with a specific username, it begins by printing a message to indicate that the account for that username is being locked. To provide immediate feedback to the security team about the unauthorized access, the function utilizes Prioritization alert. This creates a pop-up alert on the screen displaying that the account has been locked, along with the relevant title and button. This functionality not only alerts the team but serves as an example of how automated responses can be visually represented. In our hypothetical scenario, we simulate an unauthorized access event by defining a username, malicious user, and then invoking the lockUserAccount function with it. This illustrates the critical role of automated incident response systems, enabling organizations to react swiftly and efficiently to potential threats, while reducing the likelihood of human error in manual responses. Now let's implement a function to automate our vulnerability scanning process. This function, named runVulnerabilityScan, takes two parameters, the URL of the vulnerability scanner API and an authentication token. We start by defining the headers for our API request, specifying the authorization method with a bearer token. Next, we send a post request to the scanner's startScan endpoint to initiate the scan. If the request is successful, indicated by a status code of 202, the function will print a confirmation message and return the JSON response containing the scan results. If the scan initiation fails, the function outputs an error message with the status code received. To utilize this function, you need to specify the scanner's API URL and the required API token. This setup allows for seamless integration with services like Nessus or OpenVAS for automated vulnerability management in your security framework. By employing this function, you ensure regular scanning without continuous human intervention, enabling your security team to focus on addressing any vulnerabilities identified during these scans. Now let's implement a simple logging mechanism to track security events. We start by importing the built-in logging module, which provides a flexible way to log messages from Python programs. By configuring the logging parameters with basic config, we specify that all logs will be saved to a file named security audit log at the debug level, which means it will capture all levels of log messages, including detailed debug information. Next, we define a function called logSecurityEvent that takes an event message as an argument. Inside this function, we call loggingInfo, which logs the message at the info level, suitable for general operational messages. This creates an easy way to record various security events such as unauthorized access attempts. Finally, we demonstrate this functionality with an example by calling logSecurityEvent with a message indicating that a user labeled malicious user attempted unauthorized access. This simple setup not only provides a record of significant events but can also be analyzed later to monitor trends or detect anomalies, reinforcing the organization's security posture. Now let's see how we can automate the patch management process using Ansible. In the provided Ansible playbook, we target all hosts within our network to update their software packages to the latest versions. The playbook begins with specifying the hosts, and by using the become directive, It ensures the execution takes place with elevated privileges, which is often necessary for package updates. The heart of our script lies in the tasks defined under this playbook. The task instructs Ansible to perform a distribution upgrade on all packages. This is done through the apt module, which is specifically designed for managing packages on Debian-based systems like Ubuntu. By setting the upgrade field to dist, we ensure that not only the currently installed packages are upgraded, but that any dependencies required by new package versions are also accounted for. This simple yet powerful automation ensures that systems remain up to date with the latest security patches, greatly reducing the risk of vulnerabilities due to outdated software. Scheduling this playbook to run regularly can help maintain a secure and resilient IT environment effortlessly. Now let's see how we can implement a function that sends events to a SAW security orchestration automation and response tool. This is crucial for centralizing our security operations and automating incident responses effectively. We start by defining a function called sendEventToSAW, which takes three parameters: the URL of the SAW API, an API token for authentication, and the event data we want to transmit. Inside the function, we set up the headers for our API request, specifically including the authorization token in a bearer format to ensure secure access. Next, we utilize the requests library to make a post request to the SAW API's event endpoint. This request includes the event data formatted as JSON in the body of the request. The function then evaluates the response status code. If the response indicates a success, status code 200, the function confirms that the event has been sent successfully. Otherwise, it outputs an error message that includes the returned status code, allowing users to troubleshoot any potential issues. This functionality exemplifies how to integrate SAW tools within your security automation framework efficiently. As we conclude our exploration of security automation best practices, it's evident that integrating tools like OpenCTI, automating incident responses, and implementing automated vulnerability scans are pivotal in fortifying an organization's defenses against threats. By leveraging Python and integrating various automation tools, security teams can enhance their ability to manage incidents while reducing the scope for human error. In summary, we've discussed the importance of automation in achieving a proactive security stance, covering essential areas like incident response, vulnerability management, logging, patch management, and centralized systems. Implementing these best practices can significantly improve your organization's capability to swiftly detect, analyze, and respond to security threats effectively. Thanks for tuning in, and remember, security is not just an IT responsibility, it's an organizational priority. Automating security tasks in Python can significantly enhance your security operations by making repetitive tasks more efficient and reducing the risk of human error. In today's lesson, we will explore how we can leverage Python to automate various security tasks, including vulnerability scanning, log analysis, incident response, and more. By the end of this session, you'll not only understand the significance of these automations, but also have practical examples to implement in your environments. So far, we've covered the importance of security automation for organizations aiming to strengthen their security infrastructure. We discussed best practices using tools like OpenCTI for threat intelligence, automating incident responses, and conducting regular vulnerability scans. Now, we will delve deeper into specific examples of how Python can be applied in these contexts, showcasing its power and versatility in security automation. Now let's implement the authentication process for the Nessus API in our Python script. We begin by importing the requests library, which is essential for making HTTP requests to the Nessus server. Here, we declare our API URL and assign our Nessus credentials, username and password, which will be used to authenticate our session. Next, we create a session object using requests session, which allows us to persist certain parameters across requests. We construct a login payload that includes our username and password, then send a post request to the session endpoint of the Nessus API. It is crucial to check the response status. If the request is successful, we will receive a 200 status code. This indicates that authentication was successful, and we can then extract the session token from the returned JSON response. This token is vital for all subsequent API requests, so we store it in a header named xCookie. However, if the authentication fails, we use the status code to inform the user that there was an issue. This foundation will allow us to interact securely with the Nessus API for our vulnerability scanning tasks. Next, we will write the code to create and launch a vulnerability scan using the Nessus API. In this step, we begin by constructing a payload that contains the necessary parameters to configure our scan, such as the unique identifier or UUID for a predefined scan template. It's important to replace your scan template UUID with the actual UUID that corresponds to your desired scan template. In the settings subsection of our payload, we provide a name for the scan labeled automated scan and specify the target hosts by listing their IP addresses in the text targets field. Once we have prepared our scan payload, we utilize the session we previously authenticated to post this information to the scans endpoint of the Nessus API. This initiates the scan creation process. After sending the request, we check the response to verify whether the scan was created successfully. If the response status code equals 200, we can confidently assert that our scan was set up correctly, and we extract the scan ID from the response to use it in subsequent API calls. If the scan creation fails, we print an error message indicating the status code received. Now let's implement a polling mechanism to monitor the scan status in real time. In this section, we use a while loop that continuously checks the scan status using the Nessus API. We perform a GET request on the scan endpoint, which returns the current status of the scan. If the status indicates that the scan is completed, we move forward to download the scan report. This is done by creating a payload specifying the desired report format, in this case CSV. The API call to the export endpoint triggers the report generation, and we receive a file ID in the response. Next, we use this file ID to make another GET request to download the report's content. The binary content is then saved to a file named scan report, CSV, on our local system. This code ensures that we not only monitor the scan's progress but also efficiently handle the report generation and downloading process. Finally, if the scan is still in progress, a message will indicate its current status, and the script pauses for a brief period before checking again, creating a smooth polling effect. Now let's see how we can automate log analysis using Python to enhance our security operations. We start by importing necessary libraries, us for file handling and ray for regex search capabilities. Next, we configure the log directory, specifying the path where log files are stored. We also define a list of alert keywords that we want to monitor, such as unauthorized, failed login, and error. Now let's implement the analyze logs function, which takes a directory as its input. Within this function, we compile the alert keywords into regex patterns for case-insensitive searching. We then traverse the specified log directory using oswalk, iterating through each file it contains. For every file, we open it and read its lines one by one. As we pause through each line, we check for matches against our compiled patterns. If a match is found, we print an alert including the matched line and the file name for context. This setup allows us to effectively identify potential security incidents from log files. By running the analyze logs function, we can perform this analysis on our log directory, streamlining the process of monitoring crucial security-related information. Now let's implement email alerts using Python's smtplib to notify administrators of significant security events detected during log analysis. We start by configuring the email alert variable, which allows us to toggle the email alerts on or off. For our email configuration, we define a dictionary called emailconfig, where we specify the SMTP server details, including the server address, port, sender's email, recipient's email, and credentials for authentication. Next, we create a function named sendEmailAlert that accepts a message as a parameter. Inside the function, we first check if email alert is enabled. If it is not, the function exits early to avoid sending unnecessary emails. If alerts are enabled, we proceed to construct the email using the MIME text class, setting the subject, sender, and recipient. The next step involves establishing a connection to the SMTP server. We use a context manager to ensure that the connection is properly handled. Inside this context, we initiate a secure connection, log in with our credentials, and send the message. If everything is successful, a confirmation message is printed, otherwise, we catch and display any exceptions that may occur during the process. This implementation allows us to proactively notify administrators of any suspicious activities captured in the logs. As we implement these automation frameworks, remember also to consider best practices. Regular updates of your scripts and dependencies are crucial to prevent any security vulnerabilities. Furthermore, always ensure your API keys and other sensitive information are securely stored, for instance, using environment variables. Another aspect to keep in mind is unit testing. Writing tests for your scripts ensures that they behave as expected and helps catch potential bugs before going live. Python has robust testing frameworks such as Unitest and PyTest that can be incredibly helpful. To sum up, Python provides us with powerful tools for automating crucial security tasks. We've covered automation in vulnerability scanning with Nessus, error checking, and monitoring through script-based log analysis. These practices not only streamline security operations but also allow teams to prioritize tasks more effectively, protecting against potential threats. In conclusion, security automation using Python is not just an option but a necessity in today's fast-paced threat landscape. By implementing the examples we discussed, you'll be well on your way to improving your security posture with Python-driven efficiencies. In our next lesson, we'll explore how to integrate threat intelligence more deeply into our security workflows, enhancing our defenses further. Thank you for joining this session. Now let's take a look at a fundamental example of using conditional statements in Python, which is essential for decision-making in our security scripts. Here we begin by defining a variable called useAuthenticated, which is set to true. This variable indicates whether a user has successfully authenticated. Next, we implement an if statement to determine the flow of the script based on this authentication status. If useAuthenticated evaluates to true, the script will display a message stating that the user is authenticated. This positive feedback is crucial in security applications, confirming that the user can proceed with their authenticated session. Conversely, if the condition is not met, the script will execute the else block, providing a message that the user is not authenticated. This is vital for user access control, preventing unauthorized actions. Using indentation instead of braces, as seen in this example, enhances readability and aligns with Python's clean coding philosophy. By mastering such conditional checks, you can effectively manage user authentication and permissions, forming a strong foundation for your security automation efforts. Next, we will write the following code to define variables for storing sensitive information such as a username and a password. In Python, you can easily create variables without explicitly declaring the data types, which allows for a faster development process. Here we define a variable named username, which is set to the string admin, and another variable called password, assign the value secure pa55 word. This approach demonstrates how Python's dynamic typing allows you to initiate and use string data types seamlessly. The flexibility of Python is particularly useful in security scripts, as you may frequently need to adapt and modify credentials without significant overhead. It's important to remember that proper handling of credentials is crucial in security applications to prevent unauthorized access. By defining these variables early in your script, you can easily reference and manage them throughout your code, ensuring efficient and secure handling of user authentication. Such practices lay a solid foundation for employing more complex functionalities in your security scripts as we move forward. Now let's take a look at how we can implement a list to manage user roles within our security script. In the code, we start by defining a list named roles that initially contains 3 roles: admin, editor, and viewer. This showcases the ordered and mutable nature of lists, which means we can modify them after their creation. Next, we use the append method to add a new role auditor to the roles list. This method is very useful in scenarios where the number of roles might change over time, allowing us to dynamically adapt the list without having to redefine it completely. After appending the new role, we print the updated list of roles, which now includes admin, editor, viewer, and auditor. This flexibility in managing roles is crucial in security scripting, as it allows your application to respond to changes in user permissions swiftly, ensuring your scripts remain relevant and functional in a constantly evolving security landscape. By using lists in this manner, you can efficiently manage user roles and permissions, crucial aspects of any security system. Next, let's implement a dictionary to manage user permissions associated with different roles. Dictionaries in Python are perfect for this purpose as they allow us to create key-value pairs, where the key represents the role and the value is a list of permissions. For our example, we define a dictionary named permissions that contains 3 roles: admin, editor, and viewer. Each role is associated with its respective permissions. For instance, the admin role has permissions to read, write, and delete. Now let's see how we can access the permissions for a specific role. By using the print function along with the role we want to check, here, the admin role, we can directly retrieve the list of permissions assigned to that role. Running this code outputs the permissions for the admin, which are read, write, and delete. This structure allows for efficient lookups when checking user access levels, making it ideal for security scripts where quick verification of permissions is crucial for maintaining safe operations in applications. Now let's see how we can implement conditional statements to control the flow of our security script based on user permissions. In this code, we first define a variable called userRole and set it to editor. This variable determines the current user's role in the system. Next, we check whether the string delete exists in the list of permissions associated with the userRole from the permissions dictionary. This demonstrates the use of conditional logic, where we use an if statement to verify the user's capabilities. If the current user has the permission to delete, the script will print a message indicating that the user has permission to delete. However, if the user role does not possess the required permission, it proceeds to the else statement and prints permission denied. This structure is vital in security scripting, as it ensures that actions that could adversely affect important data are only executed by users with appropriate permissions, thereby enhancing the overall security posture of the application. This kind of verification is particularly useful in administrative tasks where restricting access is critical to maintaining data integrity. Next, we will implement a simple for loop that will iterate through the list of roles we defined earlier. This loop acts as a fundamental construct in Python, allowing us to process each item in a collection efficiently. By using the expanded for syntax, we gain the ability to access each element in the roles list one at a time. As the loop executes, it assigns each role from the list to the variable role, enabling us to utilize this variable within the loop's body. In our case, we will use a print statement to display each role in a formatted string. This dynamic printing not only showcases how the loop works, but also emphasizes how we can easily scale our scripts. If more roles are added to the list in the future, they will automatically be included in the output during each iteration. Such an approach highlights the flexibility and efficiency of Python scripting, particularly in a security context where we might need to manage growing lists of user roles or permissions. Now let's take a look at how we can implement exception handling in our security scripts using Python's try, except, and finally blocks. This approach is essential to ensure that your script can manage unexpected situations gracefully, particularly when interacting with files or APIs. In our example, we begin by attempting to open and read a file named securitylog.txt. The with open statement is a convenient way to handle file operations, ensuring that the file is properly closed after its sweep finishes even if an error occurs. If the file is not found, the code will raise a file not found error. Instead of allowing the script to crash, we catch this specific exception in the except block, where we provide a user-friendly error message indicating that the file does not exist. Finally, regardless of whether an exception was raised or not, the finally block ensures that the message about the log reading attempt is always executed. This is helpful for logging purposes and indicates that the script has completed its attempt to read the file, allowing for better monitoring and debugging. By incorporating these exception handling techniques, you create more resilient scripts that can handle errors effectively without compromising their overall functionality. Now let's implement a function that checks if a username satisfies certain security criteria. This is important for ensuring that usernames are robust enough, as weak usernames can lead to security vulnerabilities. In the code, we defined a function called isUsernameSecure, which takes a single parameter, username. Within the function, we first check the length of the username using the len function. If the length is less than 8 characters, the function returns false, indicating the username does not meet the security requirements. Otherwise, it returns true, suggesting the username is considered secure. This simple validation helps enforce a minimum length policy, which is a common security practice. By encapsulating this logic within a function, you can easily reuse the code across different parts of your script whenever you need to check usernames. To demonstrate how the function operates, we call it twice with different username inputs. The first call uses user123, which returns false, while the second call with user12345 returns true, reinforcing the importance of strong username choices in security scripting. Now let's implement the following code to fetch security logs from a web API. First, we import the requests library, which facilitates making HTTP requests in Python. This library allows us to interact with web services easily, enabling fetching data over the internet efficiently. Next, we use the requests.get method to initiate a GET request to a hypothetical security API endpoint that returns security logs. This method returns a response object containing information about the request, including the server's response status. We then check the status code to determine if the request was successful. A status code of 200 indicates that the data was retrieved correctly. If the request is successful, we call the response JSON method, which parses the JSON content returned from the API into a Python list or dictionary. Finally, we can print the number of logs retrieved, providing an immediate indication of the amount of data available for further analysis. This structured approach allows us to harness external data sources while focusing on implementing security logic in our scripts. Now let's implement the following code to identify roles with read permissions from our dictionary of permissions. Here, we utilize a list comprehension, a powerful feature in Python that allows us to create a new list by applying an expression to each element in an existing iterable, in this case, the permissions dictionary. The expression iterates over each key-value pair, where role represents the user's role and permissions is the list of permissions associated with that role. We then check if the string read is included in the permissions list. If it is, that role will be added to the new list we are constructing. This concise approach not only makes our code cleaner and more readable compared to a traditional for loop, but also enhances performance, particularly important in security contexts where speed and efficiency can be crucial. Finally, we print the list of roles that possess read permissions, enabling us to quickly determine which users can access sensitive data. This technique exemplifies how to effectively leverage Python's capabilities for managing roles and permissions, which is fundamental in our security automation tasks. As you can see, mastering Python syntax and data types opens the door to writing efficient and robust security scripts. From understanding how to declare variables and utilize loops to implementing functions and handling exceptions, these foundational concepts will significantly improve your capabilities and efficiency. Remember, while scripting might seem overwhelming at first, practice makes perfect. So keep experimenting, building, and improving your scripts as you continue your journey in security automation with Python. In our next installment, we will dive into integrating threat intelligence into our security workflows for enhanced protection and situational awareness. Thank you for joining this session, and happy coding. Control structures and functions are fundamental aspects of Python programming that play a crucial role in automating security tasks. Understanding these components will significantly enhance your ability to create efficient and effective security scripts. So far, we learned the importance of Python syntax and data types in writing efficient and robust security scripts. We explored key concepts like variables, lists, dictionaries, conditional statements, loops, exception handling, and functions, all of which contribute to enhancing the functionality and performance of our scripts. Furthermore, we highlighted best practices, such as using libraries and optimizing performance with list comprehensions. Now we will talk about control structures and functions and see how they can transform our approach to security automation. Now let's take a look at a simple user authentication process. The code begins by prompting the user to enter their username and password, enabling interaction with the script. This input serves as a critical part of the authentication logic. Next, it checks if both the provided username and password match the predefined correct credentials of admin and secure PA55 word. If they do, the script grants access by printing a corresponding message. If the username is accurate but the password is incorrect, the script indicates an incorrect password scenario, reinforcing the importance of valid credentials. In instances where the username does not match at all, it appropriately informs the user that the user not found. This conditional structure with if, elif, and else effectively demonstrates how logical flow in programming can respond to varying user inputs. The clear separation of outputs based on these conditions is essential for both user experience and security, highlighting the role of control structures in managing access control in security scripts. Now let's see how we can implement loops to automate the process of monitoring log files for suspicious activity. In this example, we define a list of keywords that may indicate security threats such as failed login, unauthorized access, and malware detected. We also simulate a set of log lines that a security professional might encounter in real-world scenarios. Next, we set up a nested loop where the outer loop iterates through each log line, allowing us to examine each entry sequentially. Within this loop, the inner loop checks for each suspicious keyword to determine if it appears in the current log line. When a match is found, we trigger an alert by printing a message that specifies which keyword was identified and in what log entry. This structure exemplifies how to harness the power of loops to efficiently analyze large datasets, allowing security analysts to swiftly detect and respond to potential threats. By automating this process, we can ensure that vital security checks are conducted consistently, providing a critical layer of protection for systems and networks. Now let's implement the following code that utilizes control statements to enhance our log monitoring process. The code iterates through each line of a log, looking for specific patterns that may indicate suspicious activity. First, it checks if the line contains the phrase logged in. If it does, the script employs the continue statement, which effectively tells the loop to skip to the next iteration, leaving out any lines that record a user logging in. This is particularly useful in scenarios where logged-in users are not indicative of threats, allowing the script to focus on more pertinent lines. Following this, the code sets up a nested loop that examines each log line against a list of predefined suspicious keywords, such as failed login or malware detected. If any of these keywords are found within the line, an alert message is printed, highlighting the specific threat detected. This structured approach not only streamlines the analysis of server logs but also improves efficiency, as it avoids unnecessary checks and focuses on potentially harmful activities. By combining these elements, the code serves as an effective tool for real-time log analysis in a security automation context. Now let's see how we can implement a function that checks the strength of a password. The isPasswordStrong function evaluates whether a given password meets specific criteria to ensure its robustness. First, it checks if the password is at least 8 characters long. If it isn't, the function returns false, indicating a weak password. Next, it checks for the presence of at least one digit and one uppercase letter using any, which iterates through each character in the password. If either condition fails, the function once again returns false. If all criteria are met, the function returns true, signifying a strong password. This modular approach illustrates the power of functions. They encapsulate logic, making it reusable throughout the script whenever password strength verification is necessary. Following the function definition, the code prompts the user to input their chosen password. Subsequently, it uses the isPasswordStrong function to evaluate the input. Based on the return value, it informs the user whether their password is strong or weak, guiding them on best practices for password security. This functionality reinforces the importance of maintaining secure password standards in any application. Now let's implement a function that logs security alerts by capturing alert messages as part of our security automation process. The logalert function is designed to append these messages to a log file named security_alerts.txt, which helps in maintaining a record of significant events or attempts that need to be monitored. Within the function, we utilize the open method in append mode, denoted by a, which means that new alert messages will be added to the end of the file without overwriting existing content. This is particularly useful since it allows us to accumulate alerts over time without losing any historical data. Each alert message is formatted with an added newline character to ensure that every log entry starts on a new line, improving readability. Following the function definition, we can invoke logalert to log specific incidents, such as failed login attempts or unauthorized access attempts. Each time we call the function with a different alert message, it ensures that the incident is recorded in our security log, allowing for easier tracking and analysis of potential security threats. This modular approach not only enhances the script structure, but also allows for easy updates if the logging mechanism needs to change. Now let's see how we can implement a function that keeps track of failed login attempts, helping us monitor potential security threats. In this example, we define a global variable called failedattempts, initialized to 0, which will store the total number of unsuccessful login attempts. The core of our implementation is the registerFailedAttempt function, which increments this counter each time it is called. By declaring the variable global within the function, we ensure that any changes made to failed attempts directly affect the global instance, maintaining an accurate count of failures. To simulate the tracking mechanism, we employ a loop that calls registerFailedAttempt 3 times, mimicking 3 consecutive failed login attempts. After executing the loop, we can display the total count of failed attempts using a print statement. This practical demonstration emphasizes how functions can be leveraged in security scripts, not only to encapsulate and manage specific logic, but also to maintain state, making it easier to respond to potential brute force attacks effectively. Monitoring such behaviors is crucial in security contexts, reinforcing the importance of tracking and analyzing user authentication activities. Now let's take a look at how we can implement a user authentication process that not only checks user credentials but also logs any failed login attempts. The AuthenticateUser function is the core of this process. It takes 2 parameters, the username and password inputted by the user. Inside the function, we define the correct credentials for verification. Using a conditional statement, we check if the provided credentials match the expected values. If they do, the function returns a message indicating that access is granted. However, if the credentials are incorrect, it invokes the logalert function to document the failed login attempt, providing valuable information for security monitoring. This ensures that unauthorized access attempts are noted, allowing for better tracking of potential security threats. Next, we prompt the user for their username and password. This interactive part of the code allows users to input their credentials securely. Finally, the result of the authentication process is printed out, informing the user whether access has been granted or denied. This structured approach not only enhances the security of the system, but also demonstrates the effective use of functions and control structures to automate critical security tasks. As we conclude our exploration of control structures and functions, remember that these components are integral to creating efficient and robust security automation scripts. Mastery of these concepts allows you to structure your code effectively, fostering readability and maintainability while simultaneously enhancing your security tasks. In our next session, we will delve into the exciting arena of integrating threat intelligence into our security workflows. So, keep coding and stay safe. Now let's implement a simple user login function that illustrates the use of control structures in managing access attempts. The function begins by defining the correct username and password, along with a maximum number of allowed login attempts. We initialize a counter to track the number of failed attempts. Next, we utilize a while loop that continues as long as the attempts are less than the maximum allowed. Inside the loop, the user is prompted for their username and password, and if statement checks if the entered credentials match the correct ones. If the credentials are correct, the function grants access. Otherwise, it increments the attempt counter and provides feedback on the denied access. This structure ensures that the user can only try a limited number of times, enhancing security by locking the account after too many failed attempts. Such control structures effectively manage the flow of the script, allowing for dynamic responses based on user input. By following this approach, we demonstrate the importance of implementing user authentication protocols in security scripts, ultimately protecting sensitive information from unauthorized access. Now let's implement the following refined version of our login script that integrates exception handling for more robust error management. We begin by defining a function named secureLogin, which initializes the correct username and password alongside a limit on maximum login attempts. The function features a while loop that continues to prompt the user for credentials until they either succeed or reach the maximum attempts. Inside the loop, we utilize a try block to capture potential errors during input. This is where we've introduced checks to ensure that both the username and password provided by the user are of the string type. If either is not a string, we raise a value error with a clear message indicating the issue. This design choice prevents the script from crashing unexpectedly due to invalid inputs, and instead guides the user to rectify their mistakes. After validating input types, the function checks the credentials against predefined values. If they match, access is granted. If they fail, the attempt counter increases and feedback is given to the user. This approach effectively combines user-friendly error handling with security practices, minimizing disruptions and enhancing the user experience when interacting with security scripts. Now let's take a look at a function designed to validate password strength in our security automation scripts. The isStrongPassword function begins by checking if the provided password meets certain criteria. Firstly, it ensures that the password is at least 8 characters long. If not, it returns a message indicating this requirement. Next, the function checks for the presence of at least one digit, followed by the enforcement of at least one uppercase letter. If the password fails any of these checks, the function promptly returns a relevant message to guide the user towards creating a stronger password. When we call this function, we use input to prompt the user for their password and then store the returned values in strength check and message. The output message, whether affirming that the password is strong or pointing out the specific weakness, is printed to the console. This approach not only promotes good security practices by enforcing robust password creation standards, but also showcases the modularity of our code, allowing us to reuse this function in various contexts within our scripts or even in future projects. Now, let's implement a simple user management system to automate user account management effectively. We begin by establishing a dictionary called usersDB, which will function as our in-memory database for storing usernames and their associated passwords. Next, we define the adduser function, responsible for creating new user accounts. This function checks the strength of the provided password by calling isStrongPassword, ensuring that only secure passwords are accepted. If the password meets the criteria, the username and password are added to the usersDB, and a success message is returned. Otherwise, an informative message explaining the password requirements will be shared with the user. The AuthenticateUser function follows, aiming to verify user credentials. It checks whether the provided username exists in the database and compares the input password to the stored password. If both match, access is granted. Otherwise, access is denied. Lastly, we utilize these functions by adding a user and immediately authenticating that user. This practical demonstration highlights the importance of combining control structures and functions, paving the way for a robust user management system that enforces password strength and provides secure authentication. Next, we will write a function called secure authentication that manages user login attempts while utilizing our existing authenticate user function. This function is central to controlling access based on user input. It begins by establishing a maximum number of attempts, set to 3, and initializes a counter to track the current number of attempts made. Now let's see how we can implement a loop that continues prompting the user for their credentials until they either gain access or exhaust their allowed attempts. Inside the loop, the user will be asked to enter their username and password. These credentials are then validated through the authenticate user function, which checks against our user database. If access is granted, the function returns a success message. Otherwise, it increments the attempt counter and provides feedback on the remaining tries. Should the user exceed the maximum number of attempts, the function will return a message indicating that the account is locked due to too many failed attempts. This not only enhances security by limiting access, but also demonstrates how to effectively structure code for user interaction and flow control. As we conclude this exploration into integrating control structures and functions into your security automation scripts, remember that these elements create a powerful combination for building intelligent, efficient, and maintainable code. The ability to dictate the flow of execution while reusing code makes your scripts more organized and easier to troubleshoot. In our next lesson, we will shift gears and dive into the exciting world of threat intelligence, learning how to incorporate relevant data into our security workflows. This addition will further enhance our automation scripts and ensure that we stay ahead of potential risks. Until then, keep coding and stay secure. In the ever-evolving landscape of cybersecurity, vulnerability scanning plays a critical role in identifying weaknesses within systems and networks. Automation of this process has become essential not just for efficiency, but for maintaining a proactive security posture. Today, we will delve into automating vulnerability scanning using Python, exploring tools, frameworks, and best practices that enable organizations to streamline their scanning processes. So far, we have learned about the importance of control structures and functions in Python for security automation. We explored how conditional statements and loops guide script execution, and how to implement error handling for unexpected inputs. Additionally, we discovered the significance of functions for modularity, allowing us to perform tasks like password validation and user authentication effectively. Now, we will cover the specifics of automating vulnerability scanning, starting from setting up our Python environment to integrating various scanning tools into our workflows. Now let's see how we can set up our Python environment by installing the necessary packages. We begin by using pip to install requests and Python nmap, which are essential libraries for handling web requests and automating the nmap scanning process respectively. This step ensures that we have all the required tools to start our vulnerability scanning project. Next, we will create a virtual environment named Vulnerability Scanner using the venv module. This isolates our project dependencies from the global Python installation, preventing potential conflicts. After creating the environment, we activate it to make sure our terminal session uses this isolated setup. It's worth noting that on Windows, the activation command differs slightly, indicating where the activation script is located. With our environment prepared, we can now harness the capabilities of nmap through the Python nmap library. This setup allows us to automate vulnerability scanning tasks efficiently, paving the way for streamlined scanning processes in a security automation context. Now let's implement a basic script for conducting a network scan using the nmap library. This script defines a function called scanNetwork that takes a target IP address as an argument. Within this function, we instantiate the PartScanner class provided by the nmap module, which enables us to interact with the nmap tool programmatically. The critical line in our code is the scan method, where we scan the specified target IP across a defined range of ports, in this case, ports from 20 to 1024. After performing the scan, we iterate through all detected hosts using all hosts and print their details, including the host IP and hostname. For each host, the code further investigates each protocol available, accessing the corresponding ports and printing their status, whether they are open or closed. Finally, in the main block, we specify a target IP address in CIDR notation and call the scan network function, allowing us to easily customize the target network for our scans. This foundational script not only performs basic connectivity checks, but also lays the groundwork for more advanced vulnerability scanning tasks. Now let's take a look at how we can enhance our scanning script by incorporating error handling and logging features. Here we start by importing the necessary libraries, nmap for interacting with the nmap tool and logging for tracking error messages. The logging configuration writes messages to a file named scan.log, which is essential for debugging and monitoring the script's execution. Next, we define a function called scanNetwork, which accepts a target IP address. Inside this function, we enclose our scanning logic within a try block to catch any unexpected errors. The nmap port scanner class instantiates a scanner object, and we attempt to scan the specified port range from 20 to 1024. For each host found during the scan, we print its details, including its hostname and the state of each scan port. If an exception occurs at any point during the scanning process, the except block handles it by logging the error message and informing the user that an error has transpired. This structured approach not only strengthens the functionality of our script, but also equips us with the tools to troubleshoot issues effectively. Now let's see how we can implement a function to authenticate with the Nessus API. This function named startNessusScan takes the API URL access key and secret key as parameters. The first step is constructing the login URL by appending session to the API URL. We then specify the headers to indicate that we're sending JSON data. The payload consists of our access and secret keys, which authenticate the session. Next, we use the requests library to make a post request to the login URL, sending our payload along with the configured headers. If the authentication is successful, which is indicated by a status code of 200, we extract the token from the response and print a success message. If the authentication fails, an error message is printed, signaling that the process did not succeed. To use this function, we simply call it with the appropriate API URL and our authentication keys. This step is crucial as it establishes the necessary credentials to access the Nessus API, enabling us to programmatically initiate vulnerability scans and retrieve their results within our broader vulnerability management strategy. Now let's implement the function that will create a new scan within the Nessus environment. This code is structured to send a post request to the Nessus API, utilizing the authentication token acquired earlier. It begins by establishing the scan URL based on the provided API URL, ensuring that it correctly points to the scan's endpoint. Next, we configure the HTTP headers, including the authentication token and content type. The payload, crucial for defining the scan parameters, includes a UUID placeholder that you should replace with your specific scan template's UUID. Additionally, you can customize the scan settings, such as naming the scan and specifying the target IPs. After assembling the request details, the script sends the post request. It checks the response status code to confirm whether the scan creation was successful. If the creation is successful, the code prints a success message. Otherwise, it informs you that the scan creation failed. This function encapsulates the process of initiating a scan, setting the foundation for automated vulnerability assessment with Nessus. Now let's implement a visualization function that displays the results of our vulnerability scans. This function, visualizeScanResults, takes a list of tuples as input, where each tuple contains a vulnerability ID and its corresponding severity level. We begin by creating an empty dictionary to store the vulnerabilities, iterating through the results to populate this dictionary with the vulnerability ID as the key and the severity as the value. Next, we proceed to visualize this data using a bar chart, which is a straightforward yet effective way to represent the severity of vulnerabilities. Using Matplotlib, we plot the keys of our dictionary on the x-axis and the values on the y-axis. We also add labels to the axes and a title for clarity. Finally, by calling PLT_show, we display the chart, allowing security teams to quickly assess the frequency of vulnerabilities and prioritize their remediation efforts based on severity. This visual representation is pivotal for vulnerability management, making it easier to understand where attention is needed most in a network. As we wrap up our discussion on automating vulnerability scanning, remember that integrating vulnerability scans into broader security workflows is critical. By continuously monitoring for vulnerabilities and remediating them promptly, organizations can significantly enhance their security posture. Advanced practices such as continuous compliance monitoring, integration with incident response frameworks, and leveraging threat intelligence will further solidify your defenses. Always keep your scanning tools and scripts up to date to adapt to an ever-evolving threat landscape, ensuring that you are not just reacting to vulnerabilities but proactively managing them. Thank you for joining me in this session on automating vulnerability scanning with Python. I hope this insight equips you with the tools and knowledge to enhance your organization's security stance effectively. Integrating vulnerability scanning into security workflows is a critical step toward building a comprehensive and proactive security strategy. In this video, we'll explore how vulnerability scanning not only identifies weaknesses, but also enhances overall security posture when effectively integrated into an organization's operational routines. So far, we learned about the significance of vulnerability scanning in cybersecurity and the automation of this process using Python, including essential tools and frameworks. We established our Python environment, installed necessary packages, and created a basic script for network scanning with error handling and logging capabilities. Additionally, we explored how to authenticate and initiate scans with the Nessus API, along with the importance of visualizing scan results to prioritize remediation efforts. Moving forward, we will focus on integrating these scanning processes into broader security workflows and continuous monitoring practices. First, let's revisit the role of vulnerability scanning. You can think of it as a health check for your network and systems. Regular scans provide insights into potential exposures and vulnerabilities that could be exploited by attackers. However, the real strength of a vulnerability scan does not lie merely in running it periodically, but rather in the culture of proactive security it fosters within an organization. This proactive approach is achieved by embedding vulnerability scans within security workflows, creating continuous feedback loops that allow security teams to act swiftly in the face of emerging threats. To implement this effectively, teams can integrate vulnerability scanning tools into their configuration management systems, access control mechanisms, and incident response protocols. For example, using automation tools like Ansible, you can orchestrate vulnerability scans as part of a scheduled update process. Now let's take a look at how we can automate vulnerability scanning within our Ansible playbooks. The provided playbook snippet is designed to run a vulnerability scan on all target hosts by first ensuring that Nmap, a widely used network scanning tool, is installed. Specifically, the apt module is utilized to install Nmap, specifying its state as present to confirm that it is available on each host before any scanning. Next, we define a task that executes the Nmap scan itself. The command module is used here to run Nmap with the SV option, which detects service versions on the specified inventory hostname. The output from this scan is redirected to a log file located at /var/log/nmapscan log, allowing for easy review and troubleshooting of potential vulnerabilities identified during the scan. This structured approach not only integrates vulnerability scanning into the Ansible workflow, but also reinforces the importance of continuous security checks as part of the configuration management lifecycle, ensuring that security is a persistent focus in the deployment and update processes. Now let's take a look at how we can automate the creation of tickets in Jira based on identified vulnerabilities using Python. This script leverages the Jira API to streamline the ticket creation process for security teams. First, we define a function called createJiraTicket, which takes two parameters, issue summary and issue description. These parameters will hold the title and details of the vulnerability identified by the scan. Within the function, we establish the necessary URL for the Jira API and set up authentication using your Jira email and an API token. It's crucial to keep this information secure. Next, we prepare the headers for our API request, specifying that we are sending JSON data. The payload, formatted as a dictionary, defines the project key and the fields for the issue summary, description, and issue type. Here, we've specified that the ticket type is a bug. The script then sends a POST request to the Jira API using the requests library, with the payload containing all the necessary details for the ticket. Finally, we check the response status code to determine whether the ticket was created successfully or if there was an error in the process. This automation not only saves time but also ensures that critical vulnerabilities are tracked and addressed without delay. Now let's implement a Python script that checks the logs from an intrusion detection system, IDS, for specific alerts and initiates a vulnerability scan accordingly. This script begins by defining a function, checkedLogs, which takes the path of the log file as an argument. It opens the specified log file and reads all the lines into a list. Next, the code iterates through each line of the log, searching for the phrase specific vulnerability alert. This keyword represents an alert indicating a vulnerability that requires immediate attention. When the script detects such an alert, it prints a message to the console indicating that an alert has been found and that a scan is being initiated. Following this notification, the script executes a command using the subprocess module, which runs an nmap command to scan the IP address 192.168.1.1 for any vulnerabilities. This seamless integration allows security teams to respond dynamically to threats, enhancing their ability to protect their systems. Finally, the function is called with the log file path, enabling continuous monitoring of the IDS logs for alerts and ensuring that vulnerability management processes are closely tied to real-time events. Next, we will write a shell script that automates the vulnerability scanning process using nmap. This script, named weekly scan, sh, begins with a shebang bin bash, which indicates that the script should be run in a bash shell environment. The main command within the script is nmap sv192.168.1.1, which performs a service version detection scan on the specified IP address, 192.168.1.1. This command is crucial as it identifies running services and their versions, providing valuable information about potential vulnerabilities. The output of this scanning command is redirected using to a log file located at /var/log/nmap weekly scan log. This logging ensures that each scan's results are appended to the same file, allowing for historical tracking of vulnerabilities over time. By keeping a record of scan results, security teams can analyze trends and changes in their network security posture. Now let's see how to schedule this script to run automatically using cron. By adding a line in your crontab file, you can configure it to execute the script every Friday at midnight. This automates the vulnerability scanning process effectively, ensuring that your organization maintains continuous monitoring without manual intervention. Regular scans like this are essential in proactively identifying vulnerabilities before they can be exploited. Finally, let's touch on training and awareness as part of integrating vulnerability scanning into security workflows. It's essential that your security team not only understands how to execute scans, but also comprehends their implications. Fostering a culture of security awareness within an organization is instrumental to effectively leveraging scan data. Regular training sessions should cover how to interpret scan results, prioritize vulnerabilities based on risk, and devise actionable remediation strategies. You might also consider creating interactive workshops or simulations to enhance engagement and facilitate hands-on learning. As part of a training session, you could have participants practice interpreting sample scan results. They could explore discrepancies in scan outputs, identify critical vulnerabilities, and discuss how they would go about remediating these issues in real-world scenarios. This interactive environment prepares teams to act confidently and decisively when real vulnerabilities are discovered. In conclusion, integrating vulnerability scanning into security workflows is a strategic approach that enhances an organization's overall security stance. By embedding scans into configuration management processes, automating ticket creation, linking scans with incident response actions, continuously monitoring systems, and promoting a culture of security awareness, teams can significantly improve their vulnerability management efforts. As we've discussed today, the journey doesn't end here. It's crucial to adapt your strategies continuously, keeping pace with emerging threats while leveraging the powerful capabilities of automation and integration. Thank you for joining me in this discussion on integrating vulnerability scanning into security workflows. I hope this has equipped you with the knowledge and inspiration to implement these practices effectively in your own organizations. In today's lesson, we will delve into advanced reporting and visualization methods in automated patch management. This topic is crucial for organizations aiming to enhance their security status by presenting intricate data in a clear and engaging visual format. By transforming complex information into digestible visuals, we not only make data more comprehensible, but also empower decision-makers to take timely actions. So far, we learned about the importance of integrating vulnerability scanning into security workflows to enhance an organization's security posture. We discussed how to automate the scanning process with tools like Ansible and how to utilize ticketing systems to address identified vulnerabilities promptly. Additionally, we explored the significance of monitoring and incident response integration, as well as the need to foster a culture of security awareness within teams. Moving forward, we will focus on refining these practices and continuously adapting to emerging threats. Now let's implement the following script to visualize the distribution of patched versus unpatched vulnerabilities within an organization. First, we import the matplotlib library, which provides powerful tools for creating various types of visualizations. We define our data with the labels variable indicating two categories, patched and unpatched. Correspondingly, the sizes list contains the percentage distribution, where 75% represents patched vulnerabilities and 25% for unpatched ones. To enhance the visual appeal, we define colors for each segment of the pie chart. The explode parameter allows us to slightly separate the patched slice, making it more prominent and eye-catching. This small adjustment draws attention to the portion of the pie that signifies compliance and effective vulnerability management. Next, we set the figure size for our chart, followed by the command to create the pie chart itself. We include labels, colors, and the autopt parameter to display percentage values directly on the chart. To ensure a proper circular shape, we invoke plt axis equal. Finally, we title the chart Vulnerability Patch Status and use plt show to display it. This visualization effectively communicates the organization's patch management effectiveness, providing stakeholders with critical insights at a glance. Now let's see how we can implement a basic dashboard to visualize the status of vulnerabilities across different categories. We begin by importing the necessary libraries, specifically Plotly Express for visualization and Pandas for data manipulation. Sample data is created in the form of a dictionary, with category as one column and vulnerabilities as another, which we then transform into a data frame using Pandas. This data frame forms the backbone of our dashboard, allowing us to structure our data in a way that is easily digestible for the visualization process. We then proceed to create a bar chart using Plotly's px bar function, where we define the x-axis as category and the y-axis as vulnerabilities. The chart features color coding based on the vulnerability counts, making it visually engaging and informative. Finally, we set a title and labels for clarity, and the figshow command displays the interactive chart in a web browser, allowing users to hover over the bars for more detailed information. This interactivity enhances user engagement, empowering the security team to quickly identify areas that require attention. Now let's explore how to visualize patch management trends by creating a line graph that tracks the number of patched vulnerabilities over several months. We'll begin by importing the matplotlib library, which is essential for generating this type of visualization in Python. Next, we define our sample data, including a list of months from January to June and the corresponding number of patched vulnerabilities for each month. This data will serve as the foundation for our graph, clearly illustrating how patch compliance progresses over time. Now let's implement the plotting features. We start by configuring the figure size for better visibility and then use the plot method to create the line graph. By specifying markers that indicate the data points and selecting an appealing color, the graph becomes more engaging. We enhance the visual appeal by adding titles and labels for both axes, ensuring that viewers understand what the graph illustrates. To increase readability, we enable grid lines and ensure the x-axis ticks correspond to our months. Finally, using the show function, we display the completed graph, allowing stakeholders to quickly assess trends in patch management efforts and make informed decisions based on the visual data presented. Now let's see how we can implement a simple PDF report generator using the FPDF library to aid in compliance reporting. We'll start by creating a class called PDF that inherits from FPDF. This class will define several methods to customize the report's layout and content. The header method sets the font and displays the title of our report, ensuring it's centered at the top of each page. Next, we have the chapter title method, which formats and adds section titles with a bold font, enhancing readability. Following that is the chapter body method, which is responsible for inserting the main content of each section. It uses the multi-cell method to handle text wrapping, allowing for longer paragraphs without disrupting the layout. Once our class is defined, we can instantiate an object of the PDF class, add a page, and call the methods we've created to format and insert our content. For this example, the body of the report summarizes that the organization has successfully patched 85% of identified vulnerabilities, while also addressing the remaining percentage under compliance regulations. Finally, we output the report as a PDF named Compliance Report, PDF, which can be distributed to stakeholders as a compliance artifact during audits. Now let's explore how we can implement a simple feedback collection system to gauge team satisfaction with patch management processes. In this code, we define a function called collectFeedback, which prompts users to provide their satisfaction level on a scale from 1 to 5 regarding the speed of patch management. The function retrieves the input and returns it for further processing. Next, we create an empty list, feedback scores, to store the feedback from team members. To simulate feedback collection, we use a loop that runs 10 times, representing 10 team members providing their scores. Inside the loop, each user's input is collected via the collectFeedback function, converted to an integer, and appended to the feedback scores list. Once all scores are collected, we compute the average satisfaction score by summing the scores and dividing by the total number of responses. This average score provides valuable insights into how effectively the patch management process is perceived within the team. By analyzing this data, management can address concerns and further enhance strategies, ensuring a more responsive patch management environment. As we wrap up, let's reflect on how combining advanced reporting and visualization techniques can significantly enhance an organization's patch management efforts. By leveraging visual tools, dashboards, trend analyses, compliance reporting, and feedback loops, teams can better understand their vulnerability landscape, make informed decisions, and act swiftly to mitigate risks. The journey to effective patch management doesn't just revolve around identifying and fixing vulnerabilities. It's about continuously refining processes based on clearly visualized data. As we continue to learn and adapt to the ever-evolving landscape of cybersecurity threats, remember that clarity in reporting transforms how security teams engage with and respond to challenges. Advanced reporting and visualization are not just add-ons, they are critical components of an effective automated patch management strategy. Thank you for joining me today. I hope that you feel empowered to implement these methods in your own practices. In today's interconnected world, network security is a critical component of any organization's cybersecurity strategy. As businesses grow increasingly reliant on networked systems, the automation of network security processes becomes essential in safeguarding sensitive data and ensuring the integrity of network operations. In this session, we'll dive deep into the fundamentals of network security automation, why it's increasingly important, and how you can start implementing it for heightened security within your organization. So far, we learned about the significance of advanced reporting and visualization methods in automated patch management. We emphasize the importance of making data accessible through charts and dashboards to enable quick decision-making for security teams. Additionally, we highlighted the value of trend analysis and compliance reporting, which can help organizations track their patching effectiveness and meet regulatory standards. Moving forward, we will continue to explore how to integrate feedback mechanisms to enhance our patch management strategies. Now, we will cover the introduction to network security automation, discussing its benefits, tools, and practical examples. Now let's implement a basic network monitoring script using Python. The monitor network function creates a raw socket that captures incoming TCP packets continuously in a loop, allowing us to listen to network traffic in real time. Each packet captured is logged for analysis, providing valuable insights into network activity. Following that, we check for suspicious behavior by calling the suspicious activity function, which looks for predefined indicators, such as the presence of the string attack within the packet data. If any suspicious activity is detected, the alert security team function is triggered, notifying the security team of potential threats. Additionally, the script includes a delay with time, sleep, 1 to manage the flow of monitoring, ensuring the socket isn't overwhelmed with too frequent requests. This foundational approach emphasizes automation in security by showcasing basic packet monitoring and alert mechanisms. It serves as a stepping stone to more advanced techniques, such as implementing sophisticated analysis methods or expanding the types of suspicious activities we can detect, crucial for enhancing organizational security posture. Now let's take a look at how we can automate the process of blocking suspicious IP addresses using Python. We begin by importing the necessary modules, IPaddress for handling IP addresses and subprocess for executing system commands. The core of our script lies in the block IP function, which takes an IP address as an argument. Inside this function, we attempt to block the specified IP using the iptables command, a firewall utility in Linux, by appending a rule to drop incoming connections from that IP. If successful, we print a confirmation message. If there is an error, we catch the exception and print an error message detailing the issue. Next, we define another function, detectAndBlock, where we create a list of suspicious IPs that we would like to block. By iterating through this list, we call the block IP function for each suspicious IP address. Finally, we invoke detectAndBlock to execute the blocking process for the predefined suspicious IPs. This script efficiently demonstrates how we can enhance network security by automating the incident response to potential threats. Now let's take a look at a simple Python script that can serve as a basic vulnerability scanner. This script focuses on checking whether a specified service, such as SSH, is running on a server by determining if a particular port is open. We begin by importing the socket library, which is essential for network communication. The function scanVulnerability takes two parameters, the target IP address and the port, defaulting to 22 for SSH. Inside the function, we create a socket and set a timeout to prevent the script from hanging if the server is unresponsive. By attempting to connect the socket to the specified IP and port, we can determine whether the port is open. If the connection is successful, it prints a message indicating that the port is open and checks for vulnerabilities, simulating this check since implementing real checks requires further development. Should the connection fail, either due to a timeout or if the server refuses the connection, the function catches these exceptions and informs the user that the port is closed or unreachable. Finally, we specify a target IP and execute the function, demonstrating how this basic scanner can lay the groundwork for more intricate vulnerability assessment tools in the future. Now let's implement a simple logging mechanism to automate the monitoring of network activities. First, we configure a logger that directs output to a file named Network Activity Log, capturing events at the info level. This setup allows us to track all significant actions or incidents. Next, we create a function AnalyzeLogs that takes a log entry as input and inspects it for any signs of suspicious activity, specifically failed login attempts. The use of regular expressions enables us to search through the log entry efficiently. If a failed login is detected, we invoke the Alert Security Team function, which could be designed to notify the security team about the event. We also define a logActivity function, which is responsible for passing the activity string to our analysis function. This streamlined approach ensures that every log entry is scrutinized for security concerns before being recorded. To illustrate this in action, we simulate log activities by invoking the logActivity function with both a failed and a successful login attempt. This example encapsulates the integration of logging with automated analysis, reinforcing the importance of vigilant monitoring in network security. Now let's implement a feedback collector that enables us to gather valuable insights from our incident response processes. This code defines a class named Feedback Collector, which encapsulates the functionality to collect and log feedback from users. First, the collect feedback method prompts users to provide their feedback on the incident response. This input is essential as it allows team members to share their experiences and suggestions based on real incidents. Once the feedback is received, it is appended to a file called feedback log, txt, ensuring that responses are stored for future reference. Employing a simple text file for logging creates a historical database where we can analyze trends and improvements over time. The utility of this approach lies in its ability to inform future enhancements to our automation processes, making them more tailored to our network security needs. By expressing gratitude through a thank you message, we foster a culture of open communication. This structured approach to feedback is crucial for continuous improvement in our automated security strategies, driving better responses and a more effective security posture over time. As we conclude, it's vital to recognize that network security automation is not just about utilizing tools and writing scripts. It's about creating an agile and adaptive security posture. The integration of automation into your security practices empowers teams to respond swiftly to threats, effectively patch vulnerabilities, and maintain a secure environment. As the landscape of network threats evolves, staying ahead with automated solutions will help fortify your defenses against potential breaches. In summary, today we've covered the fundamentals of network security automation, including incident response, real-time monitoring, vulnerability management, and the importance of logging and feedback. We've also implemented Python scripts to illustrate these principles, showcasing how automation can dramatically enhance security operations. As you delve deeper into automation, remember that constant learning and adaptation are key to staying ahead of cyber threats. Thank you for joining in today, and continue to explore the world of network security automation creatively and effectively. Automating vulnerability prioritization involves using algorithms and threat intelligence to assess and rank vulnerabilities based on their severity, exploitability, and impact on the organization. In today's session, you will learn how to effectively automate the prioritization of vulnerabilities, allowing your organization to proactively manage risks and enhance security posture. So far, we learned about network security automation, which uses technology to automatically protect networks and minimize manual workloads. We discussed its benefits, such as real-time data analysis and improved incident response through automation. Additionally, we highlighted the importance of logging, monitoring, and integrating feedback loops to enhance security practices. Moving forward, we will explore more advanced strategies and tools for effective network security automation, particularly focusing on automating vulnerability prioritization. Now let's take a look at how we can simulate a set of vulnerabilities for our automation process. We start by defining a list called vulnerabilities, which contains dictionaries representing each vulnerability. Each dictionary holds 3 key attributes: an ID that uniquely identifies the vulnerability, a severity score based on the Common Vulnerability Scoring System, CVSS, and an impact level indicating the potential consequences of an exploit. Next, we will implement a function to prioritize these vulnerabilities based on their severity scores. This function will sort the list in descending order, meaning the most critical vulnerabilities will appear first. By focusing on the highest severity scores, we can ensure that our remediation efforts target the vulnerabilities that pose the greatest risk. Additionally, as we develop this function, we will create a loop that iterates through the prioritized list, displaying each vulnerability's ID, severity, and impact level. This step not only aids in understanding which vulnerabilities are most pressing, but also prepares us for the next phase of adding more complex features, such as incorporating exploitability scores and integrating threat intelligence data to enhance our prioritization algorithm further. Next, we will implement a function to prioritize vulnerabilities based on their severity scores. The prioritize vulnerabilities function takes a list of vulnerabilities as input and sorts them in descending order according to their severity values using Python's built-in sorted function. The key for sorting is defined by a lambda function that extracts the severity score from each vulnerability dictionary, ensuring that the most critical vulnerabilities are addressed first. After defining this function, we execute it with our previously created list of vulnerabilities. The function will generate a new list, prioritized list, that contains the vulnerabilities ranked in order of severity. To make this information useful, we then iterate over the prioritized list, printing out essential details for each vulnerability, including its ID, severity score, and impact level. This structured output helps security teams quickly identify which vulnerabilities require immediate remediation, ensuring that efforts are focused on the most significant risks faced by the organization. Now let's see how we can enhance our vulnerability prioritization by incorporating an exploitability score. We start by updating our vulnerabilities dataset to include an exploitability field, which quantifies how likely a vulnerability is to be exploited. For instance, each entry in the dataset now contains the severity score, impact classification, and an exploitability score ranging from 1 to 4. Next, we implement a function called calculate_risk to compute a composite risk score for each vulnerability. This function adds the severity score to the exploitability score, thereby reflecting the overall risk posed by the vulnerability more accurately. Following this, we modify our prioritize vulnerabilities function to assign the calculated risk score to each vulnerability. After scoring, the vulnerabilities are sorted in descending order based on this new risk score. This allows us to prioritize not just the most severe vulnerabilities, but those that are also highly exploitable. When we run this updated function, we gain a more nuanced view of our vulnerabilities, allowing the security team to focus on the threats that require the most immediate attention. This method significantly improves our risk management and response strategy. Now let's see how we can enhance our vulnerability prioritization process by integrating threat intelligence data. In this section, we introduce a list of known vulnerabilities actively being exploited, represented as threat intelligence. The function is_exploited checks if a vulnerability ID exists in this list, which helps us identify which vulnerabilities pose an immediate threat. Next, we modify our risk calculation in the calculate_risk function. Here, we calculate a baseline risk score by summing the severity and exploitability of a vulnerability. If a vulnerability is identified as being actively exploited through the is_exploited function, we increase its risk score by 2, thereby emphasizing the need for urgent attention on these vulnerabilities. To prioritize our vulnerabilities, we use the prioritize vulnerabilities function. This function iterates through the list of vulnerabilities, calculates their revised risk scores using our updated calculate_risk, and sorts them in descending order of risk. Finally, we display the prioritized list, detailing each vulnerability's ID, risk score, severity, and impact, allowing security teams to efficiently target their remediation efforts based on the most critical vulnerabilities currently posing threats. Next, we will implement a function called createTicket that simulates the generation of support tickets for high-risk vulnerabilities. This function takes a vulnerability object as an argument and constructs a ticket information dictionary containing key details such as a title emphasizing the urgency of the vulnerability, a description highlighting its risk score, and an impact statement. By using formatted strings, the title and description are dynamically populated with information specific to each vulnerability. Once the ticket details are defined, the function prints a message to indicate that a ticket is being created. In a real-world scenario, you would integrate this function with your ticketing system's API, allowing the automated creation of support tickets directly in the system. To apply this function, we will iterate over our prioritized list of vulnerabilities generated earlier. For each vulnerability that meets or exceeds a critical risk score threshold, defined as 10 in this case, we will call the createTicket function. This structured approach ensures that critical vulnerabilities are promptly flagged for immediate attention, streamlining the remediation process and allowing security teams to address the most pressing risks effectively. In closing, automating vulnerability prioritization is an essential strategy that empowers organizations to effectively manage and mitigate risks across their networks. By combining algorithms, threat intelligence, and automation, you can establish a clear framework for prioritizing vulnerabilities based on their severity and exploitability. The structured approach we've discussed today allows security teams to focus their efforts on the vulnerabilities that pose the greatest risk to their organization. As you consider integrating such automation into your security practices, remember the key elements: gather reliable data, enhance risk calculation by factoring in exploitability and current threat landscape, and streamline remediation through effective integration with your operational workflow. Adopting these strategies will provide a solid foundation for enhancing your organization's vulnerability management process, ensuring you remain one step ahead of potential threats. Thank you for joining in today's session. When it comes to threat intelligence integration, understanding best practices is crucial for modern organizations aiming to bolster their cybersecurity posture. This lesson will illuminate the essential steps for ensuring seamless integration of threat feeds with existing security systems for real-time data enrichment and response. So far, we learned about the importance of automating vulnerability prioritization to help organizations manage risks effectively. We discussed how algorithms and threat intelligence can be utilized to assess and rank vulnerabilities for timely remediation. Additionally, we covered how to enhance prioritization by incorporating exploitability scores and threat intelligence data into the risk assessment process. Moving forward, we will explore the integration of these insights into incident response and ticketing systems for efficient action. To kick things off, it's vital to grasp the concept of what threat intelligence is and its role within an organization. At its core, threat intelligence involves collecting and analyzing information about potential or current threats in the cybersecurity landscape. This includes understanding the tactics, techniques, and procedures used by threat actors, as well as recognizing indicators of compromise (IOCs). By leveraging threat intelligence, organizations can not only be aware of risks but also proactively fortify their defenses. When integrating threat intelligence into security systems, one of the primary goals is real-time data enrichment. Essentially, you want seamless connectivity between threat feeds, data streams containing relevant threat information, and your security tools, such as SIEM, security information, and event management systems. This integration allows for a more responsive and informed security posture, where incidents can be rapidly identified and addressed. Now let's see how we can implement a function that effectively fetches threat data from an external threat intelligence API. The fetchThreatData function employs the requests library to perform an HTTP GET request to the provided API URL. Within this function, we utilize a try-except block to gracefully handle potential errors during the API call. By calling response_raise_for_status, we ensure that any HTTP errors such as 404 or 500 statuses trigger an exception. This allows us to catch and print specific error messages without crashing the program. If the request is successful, the function returns the response data parsed as a JSON object, making it easy to access specific attributes later on. In the event of an issue, such as a network error or invalid URL, we handle those exceptions separately and return none, signaling that the data could not be retrieved. This modular approach not only simplifies error management but also lays the groundwork for integrating the retrieved threat intelligence into our security monitoring systems. Now let's see how we can implement a simple class to represent an indicator of compromise (IOC) within our data model. The indicator of compromise class encapsulates crucial attributes that define an IOC, such as its type like IP address or URL, its value a brief description, and the source from which it originates. This structured approach not only helps in organizing information clearly, but also allows for better management of threat intelligence data. Inside the class, the init method initializes these attributes when a new IOC object is created. Additionally, we've included a displayInfo method, which formats and returns the IOC's properties in a readable way. This method will be essential for displaying relevant threat information to the security team, ensuring they can quickly assess the nature of the threat. With this foundational class in place, we can proceed to enrich the IOC data with risk levels and integrate it into the incident response workflow, thereby enhancing our threat handling capabilities. Now let's implement the function to enrich the IOC data we fetched earlier. This function, enrich threat data, takes a list of threat data as input and initializes an empty list to hold the enriched results. As we iterate through each item in the threat data, we create an indicator of compromise object using relevant attributes such as type, value, description, and source. Next, we apply some logic to determine the risk level associated with each IOC based on its description. If the description contains the word high, we classify it as high risk. If it contains medium, it's marked as medium risk. Otherwise, we default to a low-risk classification. This systematic categorization allows us to prioritize our responses effectively based on their assessed severity. After determining the risk level, each IOC along with its corresponding risk level is appended to the enriched data list in a structured format. This enables better organization and quick access to critical information. Finally, the function returns this enriched dataset, ready for further integration into our security monitoring systems, paving the way for effective incident response strategies. Now let's implement the function to integrate enriched threat data into our SIEM system. This function, named Integrate with SIEM, takes the enriched data as input and iterates through each item. For every indicator of compromise IOC, it simulates a call to the SIEM system's API using a hypothetical method called send-to-SIEM, which transmits the IOC's value along with its associated risk level. As each IOC is processed, we print a message that indicates the IOC and its corresponding risk level have been integrated. This feedback is crucial as it provides real-time status updates regarding the integration process. After the API call, we check the response to determine whether the integration was successful or if it failed. This success verification is vital for operational integrity, ensuring that the security teams are alerted to any issues that may arise during the integration process. Overall, this function is an essential part of enhancing the SIEM's capacity to detect and respond to potential threats dynamically and efficiently. Now let's implement a feedback mechanism that will help us keep our threat database up to date based on the status of indicators of compromise IOCs. This function, update threat database, takes two parameters: IOC value, which is the specific indicator we want to update, and status, which indicates the current state of the IOC, whether it has been mitigated or confirmed as a threat. In this function, we introduce conditional statements to handle different statuses. If the status is mitigated, we print a message indicating that the IOC is being updated to a mitigated state in the database. This is crucial for maintaining accurate records and ensuring the organization has a reliable understanding of threats. Conversely, if the status indicates a confirmed threat, the function updates accordingly, communicating that this IOC is now recognized as a serious concern. However, should the status be unrecognized, a warning message is displayed, prompting users to verify their input. This proactive approach ensures that the threat intelligence system dynamically reflects changes in threat status, thereby enhancing the organization's ability to respond to evolving challenges effectively. Now let's implement a function designed to alert the security team when high-risk indicators of compromise IOCs are detected. This function, alert security team, takes as an input the enriched data that contains our categorized IOCs. It iterates through each item within this data, examining the assigned risk level for each IOC. When the risk level is determined to be high, the function executes a print statement that notifies the team of the detected threat. This statement utilizes the displayInfo method from the indicator of compromise class, which formats crucial details about the IOC, such as its type, value, and description, into a user-friendly output. By issuing these alerts, we enhance situational awareness within the security team, prompting them to take immediate action to mitigate potential threats. This proactive step is vital, as it allows for quicker responses to high-risk situations, thereby potentially preventing or minimizing damage caused by cyber incidents. This alert system is an essential component of our threat intelligence integration strategy, ensuring that priority risks are promptly addressed. In summary, effective threat intelligence integration is not merely about having the right technology, but also about orchestrating processes and personnel to respond to threats dynamically. Formulating a strategic approach that includes fetching and enriching threat data, integrating it with security systems, maintaining feedback loops, training teams, and activating alerts is paramount for safeguarding against today's cyber challenges. By adopting best practices for threat intelligence integration, organizations can improve their incident response times and overall security posture, transforming threat intelligence from a passive resource into a pivotal component of their security architecture. In this lesson, we've laid the groundwork for utilizing threat intelligence effectively and integrating it into your organizational security framework. With the knowledge gained here, you're now equipped to bolster your defenses and navigate the complexities of the cybersecurity landscape with confidence. Input validation is a critical component in application development, ensuring that any data inputted by users is checked for type, format, length, and structure before it is processed. This ensures data integrity and application security, protecting the system from potential threats that arise from user input, such as injection attacks or corrupted data. So far, we learned about the significance of threat intelligence integration in enhancing cybersecurity. We explored the fundamental steps for incorporating threat feeds into security systems for real-time data enrichment and response. Additionally, we discussed the importance of structured data models, enriching threat data, and establishing feedback mechanisms for ongoing improvement. Finally, we highlighted the role of training personnel and implementing alert systems to ensure effective threat response. Now we will talk about automating input validation, which is essential for any robust application that interacts with user data. First, let's dive into what input validation truly means. In simple terms, input validation is the process of verifying that the data provided by users matches the expected values before the application processes it. This could be something as simple as ensuring that an email address is in the correct format or that a password meets complexity requirements. The importance of this process cannot be overstated because it prevents applications from being vulnerable to malicious inputs that could compromise the entire system. Now let's implement a function to validate email addresses using Python. We start by importing the array module, which provides support for regular expressions. The function validateEmail takes an email string as its input and defines a regex pattern that checks for valid email formats. This pattern ensures that the email consists of alphanumeric characters, followed by an @ symbol, followed by the domain name and a top-level domain. The function uses the arrayMatch method to determine if the input email matches the specified regex pattern. If it does, the function returns true, indicating a valid email, otherwise it returns false. To test the function, we include example calls that pass valid and invalid email strings, allowing us to see the function's output directly in action. This not only demonstrates how the function works but also shows the importance of automating the validation process to ensure that user inputs maintain a specific format right at the entry point, which is crucial for data integrity. Next, we will implement a function to validate numerical inputs, specifically focusing on age. The validateAge function checks whether the input value is an integer that falls within a reasonable range of 0 to 120. This range accounts for typical human ages, helping ensure that the data entered is not only in the correct format but also sensible. By using the isInstance function, we confirm that the input is indeed an integer, addressing potential format-related errors early on. After validation, the function returns true if the age meets the criteria and false otherwise. This straightforward logic is essential in preventing incorrect data from being processed later in the application. Now let's see how we can test our function to ensure it works correctly. We will call validate age with various inputs, valid ages like 25, and invalid ones such as -5 or 130, as well as a non-integer input like a string representing a number. These test cases will help illustrate the function's robustness and ability to catch incorrect inputs, reinforcing the importance of incorporating such checks into our applications for maintaining data integrity. Now let's implement a function to validate user details contained within a dictionary. This function, validate user details, checks whether the provided user information such as email and age conforms to the validation rules we defined previously. By utilizing the validate email and validate age functions, we can ensure inputs are formatted correctly and fall within acceptable limits. In the function, we first confirm the validity of the email using validate email. If the email is invalid, the function promptly returns a specific error message, guiding the user to correct the input. Next, it examines the age field with validate age, similarly returning an error message if the input does not meet the criteria. This structure allows for easy expansion. Additional fields and their respective validation functions can be incorporated as needed, enhancing the validation process. Finally, if all checks pass, the function signifies that all user details are valid, ready for processing. This approach exemplifies how automating validation can improve user experience by providing immediate feedback and encouraging proper data entry, which is crucial in application development. Now let's implement front-end validation using HTML and JavaScript to enhance user experience by checking input before it's sent to the server. We begin by defining a simple HTML structure that includes a form for users to enter their email and age. Inside the script tag, we create a function called validateForm, which will execute upon form submission. Within this function, we first retrieve the values entered in the email and age fields using the documentGetElementById method. Next, we employ a regular expression to validate the email format, ensuring that it adheres to standard conventions. If the validation fails, an alert informs the user of the invalid format, and the function returns false, preventing form submission. Similarly, we validate the age input by checking if it is a number and falls within a realistic age range of 0 to 120. If the input is invalid, another alert is issued and submission is halted. Conversely, if all validations pass, a success message is displayed and the function returns true, allowing the form to be submitted. This method not only ensures data integrity, but also enhances user engagement by providing instant feedback. Now let's implement the following code using the Cerberus library, which streamlines the validation of structured data. First, we import the validata from the Cerberus package, which is essential for defining and enforcing our validation rules. We begin by creating a schema, a dictionary outlining the expected structure and types of our data. In this case, we specify that the email should be a string in a valid email format, while age needs to be an integer within the range of 0 to 120. Next, we instantiate the validator with our schema, which will allow us to validate documents against it. We then create a test data dictionary containing a valid email and age. Utilizing the validate method of our validator instance, we pass the test document for verification. If the input conforms to the schema, we print a success message indicating that validation succeeded. Otherwise, we output a failure message alongside specific error details. This demonstrates not only how easy it is to implement input validation using Cerberus, but also highlights the automation that frees developers from handling every edge case manually. Now let's implement a structured approach for processing user data with robust error handling. In the processUserData function, we begin by using a try block to encapsulate our validation checks. Here, we first validate the email format by calling the validateEmail function. If the email is invalid, we raise a value error with a clear message indicating the issue. Next, we validate the age by calling the validateAge function, and similarly raise a value error if the age is out of the permitted range or not a number. If all validations pass, we can proceed to process the user data, printing a message to confirm successful data handling. However, should any validation fail, our accept block catches the value error and prints an error message without crashing the application. This approach not only enhances performance by preventing unnecessary processing of invalid data, but it also improves user experience by providing immediate feedback, helping users understand what went wrong. Finally, we test the function with an example of invalid user data, showcasing how our error handling mechanism works in practice. Lastly, to wrap up our discussion on automating input validation, let's reiterate some best practices. Always validate inputs on both the client and server sides, keeping security as a priority. Provide clear and specific error messages to guide users in correcting their inputs. Make use of existing libraries and frameworks whenever possible to reduce development time and errors. By following these practices and implementing systematic automated input validations, we can enhance the reliability, security, and usability of our applications, resulting in a better experience for end users, minimizing the cups of coffee consumed debugging issues that could have been easily caught from the start. In conclusion, automating input validation is a cornerstone of developing secure and reliable applications. By implementing checks for every input field, we can ensure that only valid data is processed, which in turn protects our applications from various security threats. From simple conditionals to advanced libraries, the tools available to developers are expansive and can greatly enhance your development process. So arm yourself with this knowledge and make input validation a key part of your next project. Session management is a critical aspect of web applications, enabling them to remember users between HTTP requests in an inherently stateless environment. By effectively managing sessions, applications can provide a seamless and personalized experience for users. So far, we covered the importance of input validation in application development, ensuring user inputs maintain data integrity and security. We discussed different methods for validating various input types and explored the use of libraries like Cerberus for streamlining validations. Now we'll shift our focus to enhancing session management, diving into how it helps maintain state, improves user experience, and secures applications. Now let's implement a basic user login system using Flask that exemplifies session management. We begin by importing the necessary modules, ensuring we have access to functionalities like sessions, redirection, and URL handling. Then, we initialize the Flask application and set a secret key, which is crucial for signing the session cookies securely. Next, we define two routes, login and dashboard. The login route handles both GET and POST requests. When a user submits their username via the form, we store it in the session under the key username. This allows us to persist the username across multiple requests. Upon successful login, the user is redirected to the dashboard route. In the dashboard route, we check if the session contains the username. If it does, we provide a personalized greeting, enhancing the user experience by acknowledging their identity. If the session does not have a username, the user is redirected back to the login page, ensuring that unauthorized access to sensitive information is prevented. This flow demonstrates the core capabilities of session management, crucial for maintaining user state in web applications. Now let's implement secure cookie configurations in Flask to enhance session security. The first line of code sets the session cookie secure configuration to true, ensuring that the session cookie is only transmitted over HTTPS connections. This helps protect against man-in-the-middle attacks, as cookies will not be sent over potentially insecure HTTP traffic. Next, we configure session cookie HTTP ONLY to true, which prevents JavaScript from accessing the cookie through client-side scripts. This significantly reduces the risk of cross-site scripting XSS attacks, as even if an attacker manages to inject malicious scripts, they won't be able to access sensitive session data stored in these cookies. By combining both settings, we create a robust layer of security for user sessions, allowing cookie data to be kept confidential, thereby reducing the likelihood of session hijacking. Now, these configurations should be included in your Flask application setup to ensure that all session cookies are transmitted securely and remain protected from unauthorized access. Now let's see how we can implement session management using Redis in our Flask application. We begin by importing the necessary modules, which include Flask, the session class from the Flask session library, and Redis. Next, we initialize our Flask application by creating an instance of the Flask class. To configure session management with Redis, we set several important configuration parameters. First, we specify that the session type is Redis, enabling the application to store session data in a Redis database. The session permanent setting is set to false, which means that sessions will not be permanent by default, while session use signer is set to true to enhance the security of the session cookies. We define a session key prefix to organize and differentiate our application sessions within Redis, ensuring that they don't conflict with other applications' sessions. Lastly, we create a Redis connection by specifying the host and port, in this case, using the default host localhost and port 6379. Finally, we initialize the session with Redis by passing our Flask application instance to the session class. With this setup, not only are session variables preserved between server restarts, but we also gain the ability to scale our application across multiple servers without the risk of losing session data. Now let's implement the logout functionality, which is pivotal for any web application to effectively manage user sessions. In this part of the code, we define a route called logout that handles the user's request to log out. When a user accesses this route, the application executes the logout function. The first task of this function is to remove the user's username from the session data. This is achieved using session pop username none, which effectively eliminates any trace of the user's authenticated identity in the session. By doing so, we ensure that once the user logs out, they cannot access protected routes that require authentication without logging in again. After removing the username from the session, the function redirects the user back to the login page using return redirect URL for login. This is an important step as it not only provides a clear pathway for the user to follow after logging out, but also reinforces the application's security by redirecting them away from potentially sensitive content. By managing sessions this way, we uphold a seamless user experience while maintaining the necessary security standards in our application. Now let's see how we can implement session ID regeneration in our Flask application to enhance security against session fixation attacks. In this code, we begin by defining a route for user login, which handles both GET and POST requests. When the user submits their login credentials, we first clear any existing session data using session clear. This action ensures that any previous session information is erased, prompting Flask to create a new session ID, thereby nullifying any potential security threats related to session fixation. Next, we generate a new session ID, which we store in the session alongside the username entered by the user. This approach ensures that with each login event, the user is assigned a fresh session ID, tightly coupling their identity to their current session and providing an additional layer of protection. After storing the username, we redirect the user to their dashboard, where they can access personalized content. This method effectively safeguards users' sessions, reinforcing the overall security of the application while maintaining a seamless user experience. Now let's take a look at how we can enhance our session management by incorporating user roles and permissions. In the login route, we modify our approach to fetch and store the user's role as soon as they log in. This is done by calling a fictional function, getUserRole, which retrieves the user's role based on the username provided. We then store this role in the session alongside the username, empowering our application to make decisions based on the user's access level. Next, we implement a route specifically for admin access. Here we check whether the current session has a role attribute, and if it is set to admin, we grant access to the admin panel. This decisive check helps ensure that only users with the proper permissions can access sensitive parts of the application. If the user does not meet the required role, they receive a clear message indicating that access is denied. This approach establishes a straightforward and effective method for managing user roles securely, enhancing both application functionality and overall user experience. Now let's implement logging in our Flask application to monitor session activities for enhanced security. We start by importing the logging library, which is a built-in module in Python designed for tracking events that happen during the execution of a program. Setting the logging configuration to create an app log file ensures that all log messages with a priority level of info or higher are recorded, providing a clear audit trail. Next, we will modify the existing login route to include logging functionality. When a user submits their username and successfully logs in, we log an info message that notes which user has logged in. This log entry, formatted with the username, serves as a helpful marker for identifying user actions within the application. Similarly, we will update the logout route to CAPTCHA when a user logs out. By extracting the username from the session before clearing it, we can log a message indicating that the specified user has logged out. This tracking is crucial for detecting malicious behavior, as it allows developers to retroactively examine user activities and identify any abnormal patterns that might indicate security issues. By maintaining these logs in an app log file, you create a valuable resource for both debugging and security auditing. To sum it up, session management is a cornerstone of web application development, enabling personalization and user state maintenance in a stateless HTTP environment. Effective session management involves creating, securing, and managing user sessions while also implementing best practices to safeguard against threats. As web application developers, understanding how to manage sessions will empower us to create user-friendly and secure applications that enhance user experience across the board. By implementing the strategies we've discussed, from secure cookie practices to session expiration and monitoring activities, you lay a strong foundation for robust session management that supports growth and keeps your users safe. And remember, while coding sessions might sometimes feel like managing a party where everyone just wants to crash in, a well-handled session can be the difference between a chaotic free-for-all and a smoothly running event where everyone feels at home. Thank you for joining me in this session on enhancing session management, and I hope you feel ready to apply this knowledge in your web applications. Secure coding is essential for building robust and safe software that resists attacks and avoids vulnerabilities. In this lesson, we will delve into how to automate secure coding practices, ensuring that every line of code you write contributes to a secure application from the ground up. So far, we learned about the crucial role of session management in web applications, enabling the preservation of user data and experiences in a stateless environment. We explored essential concepts such as session creation, security measures, expiration, and user role management, along with practical implementations using the Flask framework. Additionally, we discussed best practices to mitigate risks like session fixation and the importance of monitoring session activities for security audits. Ultimately, effective session management enhances user experience and fortifies application security. Now, we will cover how automating secure coding practices can simplify the development process while enhancing application security. Now let's see how we can implement secure password storage in a simple Python script. The store password function takes a plaintext password as its parameter. Inside the function, it opens a file named passwords.txt in write mode, allowing us to save the password to this file. However, this method of storing passwords directly as plaintext represents a significant security vulnerability, as anyone who gains access to this file will see the actual password displayed openly. To demonstrate how we can identify such vulnerabilities, we will utilize Bandit, a static code analysis tool. By running Bandit on our script, it will analyze the code for potential security issues, including our insecure password storage. Bandit acts as an automated check, highlighting areas of concern and offering recommendations for improvement. For instance, a better practice would be to hash passwords before saving them, using libraries such as bcrypt. This ensures that even if the file is compromised, the actual passwords remain secure, significantly mitigating the risk of unauthorized access. Now let's see how we can implement a secure user registration form using Flask and the WT Forms library. We start by importing the necessary modules, including Flask form from Flask WTF, and relevant fields and validators from WT Forms. This setup allows us to create forms easily and incorporate validation. Next, we initialize our Flask application and set a secret key for session management. This is essential for maintaining user sessions securely. Then we define a userform class which inherits from Flask form. In this class, we create fields for username and password, applying validators to ensure the username is between 4 and 25 characters, and the password is between 6 and 35 characters. These constraints help prevent incorrect input and mitigate risks of SQL injection attacks. Now let's implement a route for user registration. In the register function, we instantiate the user form and check if it has been submitted and passed validation. If validation succeeds, we can store the user data and display a success message. Finally, we render the registration template, passing the form to be displayed. Through this approach, we effectively automate input validation, enhancing the overall security of our application. Now let's implement secure error handling in our Flask application to enhance its resilience. First, we define an error handler that responds to any unhandled exceptions that may occur during the application's execution. This handler captures the exception and logs its details, which is crucial for later investigation without exposing sensitive information to the end user. Instead of returning raw error messages that could reveal underlying system architecture, we provide a generic error message, indicating that something went wrong but without compromising security. The use of JSON for the error response allows for a consistent output format, which is beneficial when communicating with front-end applications. Additionally, we create a specific route, cause error, that intentionally raises an exception for testing purposes. This ensures that our error handler is robust enough to catch and manage unexpected issues seamlessly, promoting a more secure user experience. Overall, this implementation underscores the importance of not only detecting errors, but also managing them effectively to maintain the application's integrity and protect against potential attacks. Now let's take a look at how to implement a CI/CD pipeline using GitHub Actions to enhance our application's security through dynamic testing. In this workflow configuration, we begin by specifying that the workflow will be triggered every time there is a push to the main branch, ensuring continuous integration with every code change. The first step in the workflow is to check out the latest version of the code from the repository, allowing us to work with the most current code base. Next, we move on to installing any necessary dependencies listed in a requirements file, ensuring that our environment is fully set up before running tests. The core part of this workflow is the step where we run OWASP-ZAP for dynamic application security testing. By executing a Docker command, we launch OWASP-ZAP in a container, targeting our application's URL to scan for vulnerabilities. The output of this scan generates a test report, which provides insights into any potential security flaws uncovered during testing. This automated process adds an essential layer of security to our deployments by catching vulnerabilities early, fostering a secure coding environment as we integrate security checks directly into our development lifecycle. Next, we will write the configuration for Dependabot in a Dependabot YAML file. This YAML configuration is essential for automating the process of checking for updates to third-party libraries and packages used in your Python project. The version, 2-line, indicates the version of the Dependabot configuration format being used, which helps the system understand how to interpret the following settings. Under the Updates key, we specify details about the packages that Dependabot should monitor. The package ecosystem, Python, indicates that we are focusing on Python dependencies, allowing Dependabot to recognize and manage the specific requirements associated with Python projects. The directory specifies the root directory of your project, indicating where Dependabot should look for the dependency files such as the requirements.txt. Finally, we set the schedule interval, weekly, option instructing Dependabot to check for updates every week. This regular monitoring ensures that your application's dependencies are up to date and secure, giving you peace of mind without the burden of manual checks. With this setup, you can efficiently manage dependency security and keep your project robust against known vulnerabilities. Now let's take a look at how to integrate SonarQube into our workflow for automated code reviews. This configuration allows you to define essential parameters, enhancing the overall quality and security of your codebase. We'll start with the project key, which serves as a unique identifier for your project within SonarQube, ensuring that your analyses are correctly associated with the appropriate repository. Next is project name, where you can specify a friendly name for your project that will be displayed in the Sonar Quebec interface, making it easier for team members to identify it. The sources parameter tells Sonar Quebec where to find your source code. By setting this to a dot, you indicate that the analysis should include all source files located in the current directory. The language field specifies the programming language used in your project, which, in this case, is Python. By configuring these settings, Sonar Quebec can automate the process of checking for code quality issues, coding standards, and potential security vulnerabilities. This integration means that as you write and merge your code, you gain invaluable insights that can fortify your security posture and ensure adherence to best practices. In conclusion, automating secure coding practices is not just a luxury but a necessity in today's fast-paced development environment. From static code analysis to automating error handling and integrating security testing into CI/CD pipelines, these tools and practices streamline the development process while fortifying application security. By embracing these automated solutions, you're not just upholding the security of your applications, you're also promoting a culture of vigilant coding among your development team. As we move forward in our programming journeys, remember that every line of code carries the potential for vulnerabilities, so let's make sure we code with security in mind. With the strategies we discussed, you can develop applications that are not only functional and efficient but also secure against a backdrop of ever-evolving threats. Thank you for diving into this topic with me. Incident response, commonly known as IR, stands at the front line of cybersecurity, playing a pivotal role in swiftly identifying, managing, and mitigating security incidents to safeguard organizational assets. With the rising complexity of cyber threats, traditional methods have been challenged, forcing organizations to adopt more sophisticated approaches. One of the most effective strategies emerging in the cybersecurity domain is incident response automation. Today, we are going to delve into this crucial subject, examining its importance, benefits, and some practical implementations to enhance our understanding. So far, we learned about the importance of secure coding practices in developing resilient applications, and how automation plays a key role in minimizing vulnerabilities. We explored methods like integrating static code analysis tools, automating input validation, and implementing secure error handling to enhance application security. Additionally, we discussed the necessity of maintaining secure dependencies and utilizing CI/CD pipelines for ongoing security checks. Overall, these strategies help maintain a strong security posture while streamlining the development process. Now we will cover incident response automation and its potential to revolutionize how organizations handle security incidents. Incident response automation is not just a buzzword but a necessity in today's fast-paced digital landscape. Imagine waking up to find that your organization has suffered a massive data breach. Panic ensues as your incident response team scrambles to identify the cause and contain the damage. Traditional incident response methods are often slow and can lead to significant financial and reputational damage. This is where automation comes into play. By implementing automated IR processes, organizations can respond to incidents in real time, drastically reducing response times and potential damage. Automated systems can analyze incoming threats, categorize them according to severity, and initiate predetermined response actions without human intervention. Moreover, these systems are capable of learning from past incidents through machine learning algorithms, adapting their responses to be more efficient over time. Consider a scenario where a security incident triggers a flood of alerts. An automated response system can pause through this data, filtering out noise and isolating high-priority threats that require immediate attention. This immediacy means that security teams can focus on critical incidents rather than getting bogged down in processing lesser alerts. Now let's implement a Python script that automates log pausing to detect incidents effectively. The core of this script is the pause logs function, which reads a log file line by line in search of lines that contain the keyword error. By employing regular expressions, it captures a specific format that includes a timestamp and an error message from each relevant line. If a match is found, both pieces of information are extracted and stored in an alerts list, which is returned once the entire file has been processed. Next, we'll introduce the Alert Security Team function, which takes the alerts collected from the log parsing. This function iterates over each alert, formatting a clear and actionable message that displays the error alongside its timestamp. This simplifies communication for the security team, enabling them to respond swiftly to identified issues. Finally, by specifying a log file path and invoking these functions, we can parse logs and generate alerts in an automated manner. This demonstrates a simple yet powerful way Python can significantly enhance incident detection and response, allowing security teams to handle threats proactively. Now let's take a look at how we can implement an automated email analysis system using Python. The first step of the code involves importing the necessary libraries for email handling and making HTTP requests. The Analyze Email function is designed to process incoming email content. It starts by parsing the email content to extract the subject and the body, which holds the main message. Next, the body of the email is analyzed for URLs using a hypothetical function called extract_URLs. This function, though not defined in the provided code, would typically scan the body's text and gather any URLs for further inspection. The code then iterates over each detected URL, passing them to the check_URL function. The check_URL function is crucial for validating the URLs. It sends a GET request to each URL and checks the response status code. If the response indicates a failed request, i.e., any status code that is not 200, it triggers another hypothetical function, Notify Security Team, to alert the security personnel of the potential threat. This structured approach helps automate the response process, enhancing efficiency when dealing with suspected phishing threats in real time. Now let's take a look at how we can implement a simple malware analysis function in Python. The first step in the code involves importing the necessary modules, OS for file system operations and subprocess for executing shell commands. We define the function AnalyzeFile, which takes file path as an argument. This represents the path of the suspicious file we want to analyze. Inside the function, we specify a hypothetical path to a sandbox directory where we will isolate potential malware. The first action the function performs is to copy the suspicious file to the sandbox using a subprocess call. This ensures that we can run our analysis without affecting the main system. Next, the function executes an external script named AnalyzeMalware, sh, in the sandbox environment. This script is assumed to handle the actual analysis of the malware by observing its behavior in a safe context. Finally, the results from this analysis are processed through another hypothetical function, pause_analysis_results, which helps in interpreting the findings and allows the security team to decide on the appropriate response based on the threat level determined. Now let's see how we can implement a Python script to automate the process of identifying and blocking suspicious IP addresses based on network logs. The code begins by importing the pandas library, which is essential for handling CSV files and performing data analysis effectively. Next, we define a function called blockIP, which takes an IP address as an argument. This function simulates the action of appending the suspicious IP to a blocklist file named blockedIPS.txt. Using a simple file append operation, it ensures that each blocked IP is recorded, helping maintain an up-to-date list of threats. Following that, we move on to the main function, Analyze Network Logs, which reads from a specified CSV log file containing network traffic data. This function utilizes pandas to load the data into a data frame, making it easy to manipulate and analyze. We filter the data frame to identify unique IP addresses where an attack has been detected. By iterating over this list of suspicious IPs, we call the blockIP function for each one, effectively automating the response to potential threats. This approach illustrates how automation can enhance incident response efficiency, reducing the manual workload on security teams while ensuring timely actions against network intrusions. Best practices for implementing effective incident response automation include integrating with existing tools, customizing for specific needs, and maintaining human oversight. For example, organizations should ensure that their automated systems can seamlessly operate with their existing security frameworks to maximize effectiveness. Customized scripts allow for the unique threat landscape of each organization to be considered, and continuous monitoring and improvement of automated systems ensure they remain effective against evolving threats. While automation significantly enhances efficiency, it's vital to maintain some level of human oversight, especially for complex or unclear incidents. Human analysts should be involved in the validation of automated actions to ensure that the response aligns with the organization's security policies. This balance between automation and human intervention creates a robust incident response strategy that minimizes risk while maximizing efficiency. In conclusion, incident response automation is becoming an essential part of cybersecurity. By leveraging tools like Python systems designed for automation, organizations can drastically improve their incident response times, enhance their security posture, and ensure their resources are allocated efficiently. As cyber threats continue to evolve, integrating automation into incident response strategies will be crucial for maintaining robust defenses against these challenges. Vulnerability management is an essential aspect of cybersecurity that involves identifying, assessing, and mitigating vulnerabilities within an organization's systems. In a world where cyber threats are constantly evolving, ensuring that vulnerabilities are managed efficiently is crucial for protecting sensitive data and maintaining the integrity of IT infrastructures. So far, we learned about the critical role of incident response automation in cybersecurity, highlighting its necessity in effectively managing and mitigating security incidents in real time. We explored how automation can enhance response times and allow teams to focus on high-priority threats by automating threat analysis and response actions. Additionally, we shared practical examples of how organizations implement automation using Python to improve their incident response capabilities. Overall, automation is transforming the landscape of incident response, ensuring that organizations can adapt more rapidly to evolving cyber threats. Now we will cover vulnerability management automation and its significance in improving cybersecurity practices. Vulnerability management automation is a proactive approach that helps organizations scan for vulnerabilities, assess their potential impact, and prioritize remediation efforts. Manually managing vulnerabilities can be tedious and inefficient, especially as organizations grow and the number of systems and applications increases. Automation, on the other hand, allows for continuous monitoring and swift identification of vulnerabilities, enabling timely responses. Now let's see how we can automate the vulnerability scanning process using OpenVAS in Python. We begin by importing the subprocess module, which allows us to run shell commands directly from our Python script. The core of our implementation is the runVulnerabilityScan function, which takes a target IP address as an argument. Inside this function, we construct a command string that uses the OpenVAS Management Protocol (OMP) to execute a scan against the specified target. We use the subprocess run method to execute the command, specifying shell equals true to enable shell features. The function captures the standard output and standard error streams, which can be useful for debugging or logging purposes. After running the command, we decode the output and error messages from byte strings to regular strings for easier reading. Next, we set a specific target IP address for our scan and call the runVulnerabilityScan function, capturing its output and any errors. Finally, if errors occur, they are printed to inform the user, while successful scan results are printed to display the findings. This simple automation provides a powerful tool for security analysts to streamline vulnerability assessments without manual effort. Now that we have established a method for scanning vulnerabilities, let's see how we can categorize these findings based on their severity using the Common Vulnerability Scoring System, CVSS. We'll start by implementing the assessVulnerability function, which will take a CVSS score as input and return the urgency of addressing that vulnerability. The function operates by evaluating the supplied score against predetermined thresholds. If the score is 9 or higher, it labels the vulnerability as critical, indicating immediate action is required. Scores between 7 and 8.9 are deemed high, suggesting a significant risk that should be addressed promptly. Similarly, scores ranging from 4 to 6.9 are classified as medium, indicating a moderate risk level, while scores below 4 fall under the low category, suggesting that these vulnerabilities can be attended to later. Next, we will apply our function to a list of sample CVSS scores. As we iterate through the list, we call assess vulnerability on each score and print out its corresponding priority level. This approach not only helps in understanding the risk associated with each vulnerability, but also aids in prioritizing remediation efforts effectively. Now let's implement a simple automated patch management script using Python. This script will help streamline the process of keeping system packages updated on a Linux machine. The applyPatch function defined in the code begins by printing a message to indicate that the system packages are being updated. It utilizes the OS module to interact with the underlying operating system and execute the necessary system commands. The first command, sudo apt-get update, refreshes the package index to ensure the system recognizes the most recent versions of available packages. The second command, sudo apt-get upgrade y, upgrades the already installed packages to their latest versions without requiring further confirmation from the user due to the Y flag. Finally, upon successful execution of these commands, the script prints a confirmation message indicating that the system packages have been updated successfully. By automating the patch management process, this script reduces the need for manual updates, helps minimize human errors, and ensures a more secure and efficient environment by keeping software up to date consistently. Now let's implement the following code to automate the process of asset discovery within our network using Python and the nmap library. This script starts by importing the necessary nmap module, which provides tools for network scanning and host discovery. The main function, discoverAssets, takes a network range as an argument, initializing a new instance of the portscanner class. Within this function, we use the scan method, employing the argument sn, which instructs nmap to perform a ping scan and identify active hosts without scanning for open ports. After the scan completes, we iterate through all discovered hosts using the allHosts method. For each host, we check its state. If the host is up, meaning it is active and reachable, we print a message indicating that an active host has been found. Finally, we specify a network range, 192.168.10.24, which represents the subnet typically used in private networks, and call the discoverAssets function. This automated discovery process enables organizations to maintain an accurate inventory of devices on their network, an essential practice for effective vulnerability management. Now let's see how we can implement a reporting mechanism for documented vulnerabilities using Python. The generateReport function is designed to take a list of vulnerabilities as input and generate a structured report. Within the function, we first create a dictionary named report that contains two keys: total vulnerabilities, which holds the count of vulnerabilities in the provided list, and vulnerabilities, which stores the list itself. This organized structure ensures that all relevant information is collated into a single entity for easier access and comprehension. Subsequently, we open a file named vulnerability report.json in write mode, where we will save this report. Using the JSON dump method, we write the report dictionary to the file, formatted with an indentation level of 4 for readability. This enables security teams to maintain a detailed and easily understandable record of vulnerabilities and their remediation status. Finally, the function is called with a sample list of vulnerabilities, showcasing its functionality in generating a comprehensive report that can aid in compliance and future audits. Finally, vulnerability management is not a one-time task. It's a continuous process requiring ongoing monitoring and evaluation. Automation can significantly enhance this process by integrating with other security tools, enabling a holistic view of an organization's security posture. Techniques such as using security information and event management (SIEM) systems can centralize logging and alerting, allowing for quicker reaction times and improved analysis of security events. By combining automated vulnerability management with SIEM practices, organizations can have real-time insights into their overall security status. Integrating logs from various security products can help identify patterns or trends that signify underlying vulnerabilities. In conclusion, vulnerability management automation offers a plethora of benefits, allowing organizations to swiftly identify and manage vulnerabilities proactively. By embracing automation through continuous monitoring, vulnerability scanning, patch management, reporting, and asset discovery, organizations can significantly enhance their cybersecurity posture. As we have discussed, leveraging Python scripts can streamline many of these processes, ensuring a comprehensive approach to securing systems in today's ever-evolving threat landscape. As we move forward, remember that while automation can significantly reduce the burden on cybersecurity teams, it is essential to maintain human oversight and decision-making to ensure that automated processes align with organizational policies and risk management strategies. Thank you for engaging with this lesson. Together, we can fortify our defenses against the growing array of cyber threats. Threat hunting involves proactively searching for signs of malicious activity and vulnerabilities within an organization's IT environment. Unlike traditional security practices that rely heavily on automated responses to known threats, threat hunting dives deeper into the unknown, seeking out hidden threats before they can cause damage. In this lesson, we will explore the concept of threat hunting, the role of automation in improving efficiency and effectiveness, and practical Python scripts to help you implement threat hunting techniques in your organization. So far, we have learned about the importance of vulnerability management in cybersecurity, which involves identifying and mitigating system vulnerabilities. We explored how automation enhances vulnerability scanning, assessment, and remediation processes, thereby streamlining efforts and reducing manual burdens. Now we will cover how automation can bolster threat hunting efforts, enabling faster and more thorough investigations of potential threats. Now let's implement a Python script to aggregate log files from various sources for our threat hunting efforts. We define a function called aggregate logs, which takes the directory containing the log files as an argument. Within this function, we initialize an empty list called all logs to hold the contents of our log files. We then loop through all the files in the specified directory, checking if each file ends with the log extension to ensure we only process the relevant log files. For each valid log file, we open it in read mode and extend our all logs list with the lines read from the file, effectively combining all log entries into a single collection. This aggregation will facilitate our analysis, allowing us to easily search through vast amounts of data. After processing all the log files, our function returns the consolidated list of logs. Finally, we set the path to our log directory, call the aggregate logs function, and print the aggregated logs line by line. This setup not only automates the tedious task of collecting logs, but also provides a foundation for more in-depth analysis as we search for anomalies or indicators of compromise. Next, we will implement a function to detect failed login attempts, which can indicate potential malicious activity. The detect failed logins function starts by initializing an empty dictionary to keep track of users and their corresponding failed login counts. As we iterate through each log entry, we look for the phrase failed login. For every identified instance, we extract the user from the log using a helper function, extract user from log. This function assumes a specific log format to parse the user's information easily. If a user's failed login count exists in our dictionary, we increment that count. Otherwise, we initiate a new entry for that user with a count of 1. After processing all logs, the function returns a new dictionary, but only includes users who have exceeded a threshold of 5 failed login attempts, thus flagging them as suspicious. This targeted approach helps security teams identify which users may need further investigation. Finally, we print out the detected suspicious logins, illustrating the user and their total failed attempts, facilitating swift action against potential threats. Now let's see how we can enrich the identified suspicious logins with contextual threat information using a fictional threat intelligence API. We start by defining the check threat intelligence function, which takes an IP address as input and sends a GET request to the API. If the response status is successful, it returns the paused JSON response containing relevant threat data. Otherwise, it returns none. This function acts as a vital source of contextual intelligence that can help us understand the severity of the detected anomalies. Next, we define the enrich suspicious logins function. This function iterates through the suspicious logins, comprised of user identifiers and failed login counts, and extracts the related IP address using a placeholder function called extract IP from user. It then utilizes the check threat intelligence function to obtain any threat information linked to that IP address. The enriched data, containing both the count of failed attempts and the threat information, is stored in a dictionary for each user. Finally, we invoke this enrich process and print out the enriched logs, providing threat hunters with a clearer picture of the potential severity associated with suspicious activities, thus enhancing their situational awareness and response strategies. Now let's implement the automation necessary to isolate a compromised endpoint based on insights gained from our threat hunting efforts. The isolate endpoint function accepts an IP address as an argument and simulates the isolation process by printing a message to the console. In a real-world scenario, this function would contain code to interact with your network management API, utilizing framework-specific commands to effectively quarantine the endpoint. Following the function definition, we proceed to analyze the enriched logs collected from our previous anomaly detection efforts. By iterating over each user and their associated data, we check if there is any threat information available and whether it has been identified as malicious. If the conditions are met, the script calls the isolate endpoint function with the user's IP address extracted via the extract IP from user method. This automated response is crucial, as it allows organizations to quickly mitigate threats by isolating compromised machines, thereby preventing further damage while the incident response team investigates the situation. This process exemplifies how automation can enhance the effectiveness of threat hunting and incident management through timely action. Now let's implement a function that will help us analyze previously hunted incidents to derive valuable insights. We'll use the pandas library to create a data frame from our incident data, which allows us to easily categorize and manipulate the information. In the function analyze incident data, the first step is to convert the input list of incident data into a pandas data frame. This makes it possible to leverage powerful data manipulation techniques. Following this, we group the data by threat type, which allows us to count the number of occurrences for each type of threat. This grouping is essential because it helps identify trends in your security incidents over time. After processing the data, the summary of incidents is printed, showcasing how many times each threat type has been detected. This analytical approach not only streamlines the review process, but also empowers security teams to refine their threat hunting strategies based on past incidents. By integrating this analysis into your ongoing security efforts, you can continuously adapt and enhance your detection mechanisms, improving your overall threat hunting effectiveness. Now let's implement functionality to generate automated reports from our enriched threat data, which can greatly enhance transparency and facilitate collaboration among security teams. The generate report function serves this purpose by creating a CSV file that neatly formats the information for easy dissemination. In this function, we first define the parameters: data, which holds our enriched threat information, and an optional filename parameter that defaults to threat hunting report (CSV). The function opens a file in write mode, ensuring that any existing content is overwritten. Using the CSV writer from the built-in CSV module, we initialize the writer and write the header row, which includes columns for user, threat count, and threat info. Next, we iterate through the data, which is expected to be a dictionary containing threat information for each user. For each user, we extract their name and relevant details, specifically the threat count and additional threat information, and write these as a new row in the CSV file. Finally, upon invoking the generate report function with our enriched logs, a structured report is produced and saved, thus streamlining the process of sharing vital threat insights with the security community. As we conclude our discussion on threat hunting automation, remember that while the tools and techniques we covered are powerful, the human factor remains critical. Threat hunting is not solely about scripts and algorithms. It's about leveraging human intuition and creativity to uncover the threats that technology alone cannot reveal. By combining human expertise with automated tools, you are not just reacting to threats but proactively hunting them down. In summary, threat hunting automation provides an innovative and invaluable approach to securing your environment. We covered the importance of data aggregation, anomaly detection, threat intelligence enrichment, automated response, and continuous improvement through analysis. By implementing Python scripts and automation in your threat hunting efforts, you will be well equipped to hunt down threats before they have a chance to impact your organization negatively. Thank you for joining us in this lesson, and stay safe out there. In modern cybersecurity, machine learning (ML) and artificial intelligence (AI) are fundamentally changing the landscape by enhancing our ability to detect and respond to threats with unprecedented speed and precision. Today, we'll explore the revolutionary role of AI in cybersecurity, covering not just the principles but also practical applications using Python code examples. So far, we've covered the importance of a proactive approach to threat hunting and how automation improves efficiency by identifying vulnerabilities. Now, we'll delve into the exciting world of AI and its critical contribution to modern cybersecurity solutions. Next, we will implement the necessary Python code to create a supervised learning model that identifies benign versus malicious network activity. We start by importing essential libraries, including pandas for data manipulation and scikit-learn for our machine learning model. The first step is to load our dataset, which contains network traffic information, and we specifically target the column labeled label to differentiate between benign 0 and malicious 1 activity. Now let's prepare our features and labels by separating them. We drop the label column to isolate the features while the labels are assigned to the Y variable. After this, we proceed to split the dataset into training and testing sets. This division ensures that we can train our model on one subset while evaluating its performance on another to avoid overfitting. Next, we create a support vector classifier (SVC) model using a linear kernel and fit it to our training data. After the model is trained, we make predictions on the test set and compute the prediction accuracy using accuracy score. Finally, we print out the accuracy, which indicates how well the model distinguishes between benign and malicious traffic, enabling proactive threat management in cybersecurity. Now let's see how we can implement an anomaly detection algorithm using the isolation forest method in Python. First, we begin by importing the required library, isolation forest, from scikit-learn's ensemble module. Then, we load the preprocessed network traffic data from a CSV file, ensuring that the dataset is suitable for our analysis. Next, we separate the features from the dataset, using all columns except for the last one, which may contain the target variable. This step is crucial because it allows the model to focus on the relevant input data without being influenced by labels. We then initialize the isolation forest model, specifying a contamination parameter that indicates our expectation of how much of the data may be anomalous. In this case, we set it to 5%. After fitting the model to the features, it learns to identify patterns within the data. Following the training phase, we use the model to predict anomalies by calling the predict method. The predictions will yield -1 for anomalies and 1 for normal observations. Finally, we extract and display the anomalous data points, allowing security teams to investigate potentially malicious activities before they escalate into more significant threats. Next, we will implement a supervised machine learning approach using a support vector machine (SVM) model to classify the severity of cybersecurity incidents. First, we load our incident data and the corresponding severity labels from CSV files, ensuring we have the necessary information to train our model effectively. To optimize our model's performance, we split the combined dataset into training and testing sets, allocating 70% for training and 30% for evaluation. This helps us validate the model's accuracy on unseen data. Now let's create an SVM instance with a linear kernel and fit it to our training data. which means the model will learn to distinguish between different severity levels based on historical incident data. Once we've trained our model, we make predictions on the test set to classify the severity of each incident. Next, we implement response mechanisms based on predicted severity levels. By examining the predictions, we can initiate specific actions. For instance, high-severity incidents trigger an automatic response indicating an urgent need for action, while medium and low-severity incidents may prompt notifications or simple monitoring. This automatic prioritization enhances incident response efficiency and demonstrates the model's practical utility in real-world cybersecurity scenarios. As we proceed, it is paramount to understand the ethical implications and challenges of deploying AI within cybersecurity. While AI-driven solutions offer tremendous benefits, they also raise concerns related to model bias, explainability, and data privacy. AI models often act as black boxes, where their decision-making process is not transparent. This opacity can compromise trust and lead to erroneous conclusions if not properly managed. Moreover, data used for training models must be accurate and diverse. Otherwise, biases present in the input dataset can skew results, leading to false positives or negatives. Thus, it is critical for organizations to establish robust data governance practices and ensure AI solutions comply with data privacy regulations, including GDPR General Data Protection Regulation and CCPA, California Consumer Privacy Act. In summary, AI and ML are not just trends in cybersecurity. They are essential components pushing the industry toward advanced threat detection, rapid incident response, and effective preventive measures against cyber threats. By leveraging these powerful technologies, organizations can stay ahead of the evolving landscape of cybersecurity challenges. Thank you for joining this journey into the world of AI in cybersecurity today. We have discussed a variety of applications, practical coding examples, and the importance of ethical considerations. In our next lesson, we will dive deeper into the specific algorithms used in machine learning that shape the future of cybersecurity solutions. Stay tuned. Now let's implement a support vector machine model to classify network traffic as benign or malicious. We start by importing the necessary libraries, including pandas for data manipulation and the scikit-learn modules for model training and evaluation. Following this, we load our dataset containing labeled network traffic data using pandas, ensuring that our features and labels are correctly assigned. The features consist of all columns except the label, while the label column indicates whether each instance is benign 0 or malicious 1. Next, we split the dataset into training and testing subsets to evaluate the model's performance accurately. This is done using the train-test-split function, which allows us to train our model on a portion of the data while reserving another portion for testing its accuracy. We then create a support vector classifier model with a linear kernel, which is suitable for this binary classification task. After training the model on the training data, we make predictions on the test set and calculate the accuracy using the accuracy score method. Finally, we print the model's accuracy as a percentage, providing insights into its performance in correctly classifying network traffic based on our historical data. Now let's see how we can implement anomaly detection using the isolation forest algorithm in Python. First, we begin by importing the isolation forest class from the scikit-learn ensemble module. Next, we load our preprocessed network traffic data from a CSV file, which contains features extracted from the network traffic analysis. After loading the dataset, we isolate our features by selecting all columns except the last one, which often contains labels. This step is crucial as we want the model to learn solely from the features of the data that help identify anomalies. Following this, we create an instance of the isolation forest model, specifying a contamination parameter of 0.05, indicating our assumption that approximately 5% of the data may consist of anomalies. Now we fit the model with the feature data, allowing it to learn the underlying patterns. Once trained, we use the model to predict anomalies within the same feature dataset. Anomalies are indicated by a prediction of -1, while normal instances are marked as 1. To facilitate further investigation, we extract the rows of the original dataset that have been flagged as anomalous based on our predictions. Finally, we print out these anomalous data points for examination, enhancing our ability to detect potential threats in real time. Now let's implement a system for automated response to cybersecurity threats using machine learning. We begin by importing necessary libraries, such as pandas for data manipulation and the random forest classifier from scikit-learn for our classification model. The first step is to load the incident data and their corresponding severity levels from CSV files. The severity levels are labeled from 0 to 2, where 0 indicates low severity, 1 is medium, and 2 signifies high severity. Next, we split the dataset into features and labels, with the incident data as features and the severity levels as labels. To ensure our model can generalize well, we divide the data into training and testing sets, allocating 30% of the data for testing purposes. Now we create our random forest classifier model and fit it to the training data. This process enables the model to learn how different incident features relate to severity. Following this training, we make predictions on the unseen test data. To implement automated responses based on those predictions, we loop through each severity level identified. Depending on the level classified, we print different responses. For high severity, we might initiate immediate isolation. For medium, notify the security team, and for low severity, simply monitor the incident. This structured approach ensures quick and effective responses to various types of cybersecurity incidents. Now let's see how we can implement basic data validation and cleansing using Python with the pandas library. First, we begin by loading our dataset, which we assume contains network traffic information. To ensure the integrity of our data, we check for any missing values in each column. This step is crucial because missing data can significantly impact the performance of our machine learning models. We then print out the number of missing values per column for easy identification. Next, to handle any missing values in numerical features, we fill these gaps with the median of the respective columns. This approach mitigates potential biases that could arise from simply discarding rows with missing data, thereby preserving as much information as possible. After dealing with missing values, we turn our attention to duplicate entries. We remove any duplicates that may skew our modeling process, ensuring the data remains unique. Lastly, we examine the data types of the columns to verify their correctness. Properly structured data types are essential for appropriate analysis and modeling in machine learning. This validation and cleansing process lays the groundwork for building reliable and accurate machine learning models that can enhance our cybersecurity efforts. In conclusion, machine learning plays a transformative role in enhancing threat detection capabilities within cybersecurity. Its applications extend from advanced threat detection and anomaly detection to automated incident response. By leveraging various algorithms and ensuring data integrity, organizations can heighten their security posture in an increasingly complex cyber landscape. As we move forward, it's important to understand the ethical implications and challenges surrounding the deployment of these technologies. There will always be biases and privacy concerns to manage in regular intervals to ensure ethical compliance in systems utilizing machine learning. Thank you for joining today's discussion on the applications of machine learning in threat detection. I hope you feel more equipped to handle discussions about utilizing AI and ML in cybersecurity. In our next lesson, we will explore the specific machine learning algorithms that enrich cybersecurity solutions further. Stay tuned. In today's lesson, we'll dive into the exciting world of automating incident response with Python. Specifically, we'll explore how integrating AI into security information and event management, or SIEM systems, can significantly streamline the identification, containment, and resolution of security incidents. So far, we learned that machine learning significantly enhances cybersecurity by improving threat detection and response times. We've explored applications like automated threat detection, anomaly detection, and incident response, focusing on practical implementations using Python. Additionally, we've emphasized the importance of data integrity and ethical considerations when using AI in the cybersecurity domain. Now, we will cover how to automate incident response workflows using Python, increasing our security posture and response efficiency. Now let's see how we can implement a Python script to send an alert email whenever a security incident is detected. This code establishes a connection to an SMTP server using the smtplib library, which is essential for sending emails from Python. Here, we define a function called sendAlert, which takes in the email recipient's address and a description of the issue at hand. Within this function, we specify the SMTP server details, such as the server address, port, and the credentials needed to authenticate the sender. By utilizing the MIME-text class from the email MIME-text module, we create the email message, including the subject, sender, and recipient fields. The try block allows us to handle potential errors gracefully while performing operations such as logging into the SMTP server, sending the email, and quitting the session. If everything goes smoothly, the function prints a confirmation message indicating that the alert has been successfully sent. However, in case of any exceptions during the sending process, an error message is printed, helping us diagnose issues related to email notifications. This automated alerting mechanism is crucial in a cybersecurity incident response framework, ensuring relevant personnel are notified promptly. Now let's see how we can implement the isolation of a workstation suspected of malware infection using Python. We begin by importing the subprocess module, which allows us to execute shell commands directly from our script. The primary function, isolateSystem, takes an IP address as an argument. Inside this function, we construct a command string that utilizes the netch utility to block all outgoing network traffic for the specified IP address. This command effectively isolates the affected system from the network, thereby containing the potential threat. Next, we use subprocess run to execute the command, setting the shell parameter to true to indicate that it should be run in the shell environment. We also enable the check parameter, which will raise an error if the command fails. If the command executes successfully, we print a confirmation message indicating that the system has been isolated. However, if there is an error during execution, a called process error is caught, and we output an error message. This approach not only automates the isolation process, but also ensures that any issues encountered are appropriately handled, making it a reliable component of our incident response workflow. Now, let's see how we can implement a function to automate the deletion of a malicious file detected on a machine. The code begins by importing the necessary libraries, OS for interacting with the operating system, and path from the pathlib module for convenient file handling. We define a function called delete malicious file that takes a file path as its parameter. Inside the function, we utilize a try-except block to handle any potential errors gracefully. We first create a path object using the provided file path, which allows us to easily check if the specified file exists. If the file does indeed exist, we proceed to remove it using osRemove, which deletes the file from the system and confirms successful deletion through a print statement. If the file does not exist, an appropriate message is displayed. In case of any unexpected issues during the deletion process, such as permission errors or if the file is in use, the exception handling catches these errors and prints an error message for troubleshooting. This functionality is a vital step in incident response, enabling organizations to automatically mitigate risks by swiftly eliminating potential threats from their systems. Now let's see how we can implement a function to generate an incident report using Python and the pandas library. This function, generateIncidentReport, begins by reading incident data from a specified CSV file. The pd_read_CSV file path function call loads all the incident records into a pandas data frame, which allows for easy data manipulation and analysis. Once the data is loaded, we calculate the total number of incidents using the len function, which counts the number of rows in the data frame. Additionally, we filter the data frame to identify unresolved incidents, those with a resolution status marked as unresolved. This is done by using Boolean indexing, which allows us to create a new data frame that only includes unresolved incidents. Finally, we print out key summary metrics, including the total number of incidents and the count of unresolved ones. We also display details of the unresolved incidents, specifically the timestamp, severity, and description columns, providing critical insight into the current status of incidents. This functionality is vital for security teams to assess ongoing situations and make informed decisions on prioritizing their responses. Now let's implement a function that encapsulates our entire incident response lifecycle. This script, named handleIncident, serves as the orchestration point for the automated incident response process. First, we initiate the response by sending an alert to the security team whenever suspicious activity is detected. The send alert function, which we defined earlier, takes care of notifying the responsible personnel via email, ensuring they're informed about the incident promptly. Next, the script isolates the affected system to prevent further damage. This is executed by the isolate system function, which blocks outgoing traffic to the specified IP address, effectively containing the threat. Following isolation, we address the potential threat by removing any malicious files. The delete malicious file function is called with the path to the detected file, allowing for the automated cleanup of harmful elements. Finally, the incident response process concludes with generating a comprehensive report through the generate incident report function. By logging the incident details into a CSV file, we facilitate the assessment of the incident and any unresolved issues, providing valuable insights for future responses. This modular and systematic approach ensures that each phase of incident management is executed seamlessly, enhancing both efficiency and effectiveness in responding to security threats. In conclusion, automating incident response using Python is a powerful way to enhance an organization's cybersecurity posture. From alerting teams to isolating affected systems and remediating threats, automation enables a swift and coordinated response to security incidents. By integrating these Python scripts with existing SIEM systems and tools, organizations can not only save time, but also reduce the likelihood of human error when responding to incidents. Moreover, automation paves the way for better analysis and reporting, allowing security teams to understand threats and refine their defenses. As the cybersecurity landscape continues to evolve, the integration of AI and automation into incident response workflows will become increasingly critical. As we have learned today, harnessing the capabilities of Python provides an excellent foundation for developing robust incident response strategies. Thank you for joining me today as we explored automating incident response with Python. Stay tuned for our next lesson, where we'll dive deeper into specific machine learning algorithms that can further enrich cybersecurity solutions. Until next time. In today's rapidly evolving cybersecurity landscape, automation has become a key enabler for security teams to stay ahead of sophisticated threats. The integration of automated systems into cybersecurity strategies not only boosts efficiency, but also enhances the ability to manage diverse security challenges effectively. Now we will implement the code to prepare our dataset for anomaly detection using the isolation forest algorithm. First, we import the necessary libraries, including pandas for data manipulation and scikit-learn for machine learning. We load our dataset of historical security events, which contains various features relevant to security incidents. It's important to separate the features and labels. Features will be used for training our model, while labels indicate the nature of each event, whether it's benign or malicious. Next, we split the dataset into training and testing sets, which is a critical step in validating our model's performance. We'll allocate 80% of the data for training and 20% for testing, ensuring we have unseen data for evaluation. After splitting, we initialize the isolation forest model, configuring it with a contamination parameter to specify the expected proportion of anomalies in our dataset. We then fit the model on the training set, allowing it to learn from the characteristics of normal and abnormal instances. Finally, we make predictions on the test set. The model outputs values indicating whether each instance is considered an anomaly or normal. To simplify the results, we convert these outputs into a more human-readable format, where anomalies are labeled as 1 and normal instances as 0. This process establishes a foundation for detecting security threats effectively through automation. Now that we have trained our anomaly detection model, it's essential to evaluate its performance to ensure it can accurately identify threats. Next, we will implement the confusion matrix and classification report from the scikit-learn library, which are valuable tools for assessing our model's efficacy. We begin by importing the necessary functions from the sklearn metrics module. The confusion matrix provides a summary of the prediction results by showing the counts of true positive, true negative, false positive, and false negative predictions. To gain deeper insights into the model's performance, we leverage the classification report, which includes metrics such as precision, recall, and F1 score. These metrics help us understand the balance between correctly identified anomalies and those missed or incorrectly classified as normal. Now let's write the following lines to display our evaluation results. By executing this code, you'll generate a comprehensive matrix and report that highlight where our automation is effective and where there is room for improvement. This analysis is crucial as it directly informs our next steps in refining our model, including adjustments to data collection and feature engineering to enhance our detection capabilities further. Now let's see how we can implement an automated alert enrichment process using Python. The code begins by importing the request library, which allows us to make HTTP requests to external APIs conveniently. We define a function called enrichAlert, which takes an IP address as an argument. Inside this function, we construct a URL to access a hypothetical threat intelligence platform API, specifically formed to retrieve data about the given IP address. Next, the function sends a GET request to this URL to fetch threat intelligence data. If the request is successful and the server responds with a status code of 200, the function processes the response by returning the enriched data in JSON format. This enriched data can provide valuable insights, such as threat levels and associated risks, enabling security analysts to make more informed decisions about the severity and relevance of an incident. If the response indicates an error, the function gracefully handles it by returning a dictionary with an error message, indicating that the enrichment process has failed. This automation not only enhances efficiency in incident responses, but also aids security teams in prioritizing their actions based on real-time threat data. Now let's implement the following function to automate the response to potential threats by blocking malicious IP addresses. We start by defining a function named blockIP, which takes an IP address as an argument. Inside the function, we specify the URL of our firewall's API endpoint that handles IP blocking requests. Next, we construct a payload, a dictionary that formats the IP address into a JSON-compatible structure for the API request. Using the requests library, we send a post request to the firewall API with the constructed payload. The response from the server will indicate whether the blocking action was successful. We evaluate the response's status code, returning true if the IP address is successfully blocked, which allows us to implement a mechanism for immediate response in the face of detected threats. To demonstrate how this function can be used, we introduce an example scenario where we check the count of anomalies detected in previous predictions. If there are more than 10 instances of suspicious activity, we loop through a list of suspicious IPs. For each of these IP addresses, we call the blockIP function, automating the process of blocking potentially harmful IPs and ensuring our network's security is maintained in real time. As we navigate through the landscape of cybersecurity, understanding the importance of automation can ensure we remain one step ahead of cyber threats. The constant advancements in technology mean that automation strategies must evolve accordingly. In summary, automation in cybersecurity is a multifaceted approach involving the integration of machine learning for anomaly detection, threat intelligence enrichment, and automated incident response. Security teams are equipped with tools that bolster their operational capabilities, significantly reducing the time spent on repetitive tasks while improving the accuracy and effectiveness of threat detection and response. Now that we've established the essential role of automation in cybersecurity, the next step could be diving into how to implement continuous learning systems where automated solutions evolve with emerging threats. Let's keep pushing the boundaries of what we can achieve in cybersecurity through innovative automation techniques, ensuring the safety of our digital world. As cyber threats grow in both volume and sophistication, timely and efficient threat response has become a cornerstone of effective cybersecurity. Today, we're diving into how we can leverage Python to enhance our threat response strategies, allowing security teams to react promptly and effectively to incidents. So far, we learned about the critical role of automation in cybersecurity, particularly how it enhances incident response, threat detection, and data analysis. We explored the integration of machine learning for anomaly detection using Python and the implementation of automated workflows in security operations. We also discussed the importance of evaluating model performance and automating the enrichment of security alerts with threat intelligence. Moving forward, we will focus on implementing continuous learning systems to adapt our automation strategies to emerging threats. Now let's see how we can implement packet sniffing using the Scapy library to enhance our threat detection capabilities. This code initializes packet sniffing, which allows us to continuously monitor network traffic in real time. The packet callback function is triggered each time a packet is captured, enabling us to analyze its contents. Inside the function, we check if the packet contains an IP layer. If it does, we retrieve the source and destination IP addresses, which are essential for understanding the communication taking place in the network. Next, we introduce a hypothetical function isSuspicious that assesses whether the source IP address is flagged as suspicious. If it is, we take immediate action by calling another hypothetical function block IP to prevent further interactions from that IP. Finally, the sniff function is called with a filter set to capture only IP packets and the packet callback function specified to process each captured packet. This simple yet powerful approach automates real-time threat detection, significantly enhancing our network security measures by allowing swift responses to detected threats. Next, we will implement a method to analyze security logs using Python's powerful pandas library. First, we begin by loading the security logs from a CSV file into a data frame, allowing us to utilize the rich data manipulation capabilities of pandas. Once the logs are imported, the first focus is to filter out entries with a status marked as failed, specifically looking for failed login attempts. This critical step allows us to pinpoint potential weak spots in our security where unauthorized access may be attempted. Now let's see how we can identify users who have experienced multiple failed login attempts. By utilizing the value counts method, we can count the occurrences of each username in our filtered data. This count helps us gauge which accounts are being targeted most frequently. Subsequently, we can set a threshold, such as more than 5 failed attempts, to flag these users as suspicious. Finally, the results are displayed, listing the usernames that have been identified as suspicious. This automated analysis significantly reduces the time security analysts spend sifting through logs, enabling them to respond promptly to potential threats and enhancing overall security posture. Now let's implement a function to automate the response to suspicious file uploads in a web application. The respond to file upload function takes a file name as its input and first checks if the file is flagged as suspicious by calling a hypothetical isSuspicious function. This initial evaluation is crucial as it determines the necessity of further actions. If the file is deemed suspicious, the function proceeds to quarantine it using another hypothetical function, quarantine file, effectively removing it from the accessible environment to prevent any potential harm. Following this, it notifies the security team through Notify Security Team to ensure they are aware of the threat. Finally, the incident is logged using logincident, documenting the event for future analysis and improving incident tracking. As a practical demonstration, we simulate a file upload event by passing a string representing a potentially malicious file, potential malware, exe, to the respond to file upload function. This comprehensive approach fosters a quick and effective response to security threats, embodying the principle of automation in enhancing cybersecurity measures. Now let's implement a simple script to analyze past incident data and evaluate the effectiveness of our threat response strategies. We start by loading our historical incident data from a CSV file using pandas, a powerful data manipulation library. This allows us to work with structured data easily. Once we have the data, we focus specifically on incidents that had a successful outcome by filtering the data frame for rows where the outcome is marked as success. This step is crucial because it helps us isolate the circumstances under which our responses worked effectively. Next, we count the different types of responses that were successful by using the value counts method on the response type column of our filtered data. This analysis not only highlights the most effective responses, but also provides insights that can guide future incident response strategies. By understanding which responses yielded the best outcomes, security teams can refine their automated systems and continuously improve their overall security posture. This process of retrospective analysis is vital in adapting to the evolving landscape of cyber threats. Now let's take a look at how we can automate vulnerability scanning using Python and the Nmap library. The code begins by importing the Nmap module, which provides an interface to the powerful Nmap network scanner, widely used for discovering hosts and services on a computer network. Next, we define a function called scanHosts, which takes a parameter IP range. Inside this function, we create an instance of Nmap port scanner, enabling us to access Nmap's capabilities. The crucial part of the function is the scan method, where we pass the specified IP range and the SV argument to perform version detection of services running on the detected hosts. After scanning the specified range, the function returns all hosts discovered in the network. In our example, we call this function with the IP range 192.168.10.24, which typically represents a local subnet. Finally, we print the list of scanned hosts, allowing security teams to understand their network layout and quickly identify potential vulnerabilities. By automating such tasks, we empower security teams to proactively address weaknesses before they can be exploited by attackers. In conclusion, leveraging Python for threat response can radically enhance an organization's cybersecurity posture. By automating traffic monitoring, log analysis, incident response playbooks, retrospective analyses, and vulnerability scanning, security teams can streamline their operations significantly. The advantage of automation lies in its ability to increase efficiency, reduce the room for human error, and allow teams to focus on more strategic tasks rather than repetitive manual processes. As we continue to refine and evolve our automation strategies, remember that the landscape of cybersecurity is ever-changing. Embracing a mindset of continuous learning and adaptability will better equip your teams to tackle the threats of tomorrow. Now that we have laid the groundwork for leveraging Python in threat response, remember, the future of cybersecurity relies heavily on automation, and Python stands as a powerful tool in our arsenal. Let's keep pushing the envelope in making our digital landscape a safer place. As security challenges grow in complexity, so too will the role of automation. Today, we embark on an exciting journey into the future trends in Python security automation, exploring how it evolves to meet increasing threats in complex environments. This session promises to be rich in information and fun as we delve into advanced automation techniques through practical coding examples. So far, we learned about the significance of leveraging Python to automate threat response in cybersecurity, including monitoring network traffic and analyzing security logs. We discussed how automation can enhance incident response through playbooks and updating processes based on past incidents. Additionally, we explored the use of Python for proactive measures, such as vulnerability scanning, to improve security posture. Moving forward, we will refine these strategies to address emerging threats effectively. Now let's see how we can implement anomaly detection using the isolation forest algorithm within our security automation framework. First, we begin by importing the necessary libraries, pandas for data manipulation and the isolation forest model from scikit-learn for detecting anomalies. The next step involves loading our network traffic data from a CSV file, which should contain important features like packet size, destination port, and time of day. These features are essential as they provide the input data model to identify any unusual patterns that might indicate a security threat. With our data prepared, we then proceed to define our isolation forest model, specifying a contamination parameter of 0.01, indicating that we expect roughly 1% of the data to be anomalies. After training the model on our selected features, we apply it to predict anomalies in the dataset. The results are then appended to our original data frame as a new column labeled Anomaly. Finally, we print the rows where anomalies are detected, allowing us to focus our attention on potential threats that warrant further investigation, thus enhancing our security posture through proactive response mechanisms. Now let's implement a function to automate the response to identified threats by blocking suspicious IP addresses. We begin by importing the requests library, which allows our Python program to make HTTP requests. The block IP function is defined to take an IP address as an argument. This function simulates a request to a fictional firewall API. When called, it posts a JSON payload containing the IP address that needs to be blocked. Upon receiving a response, the function checks the status code. If it's 200, the blocking is successful and we print a confirmation message. If not, we notify that the blocking attempt failed. Next, we define the automate response function, which accepts a list of suspicious IPs. This function iterates through each IP address in the list and calls the block IP function for each one, effectively automating the process of IP blocking. After defining both functions, we illustrate their use with an example list of known suspicious IPs. By calling automate response with this list, we can initiate the automated blocking process. This workflow reduces the manual effort needed by security teams and enhances incident response efficiency. Now let's implement a function that enriches potential threats using data from a threat intelligence platform tip. The function enrichThreat takes an IP address as input and makes a GET request to a hypothetical threat intelligence API, which acts as our data source. If the API returns a status code of 200, indicating a successful response, the function will pause the JSON data it receives and return it, providing enriched information related to that IP address. This is crucial for security analysts, as the additional context around a suspicious IP can help them better assess threats. Conversely, if the API call fails or returns an error, the function will return none, indicating that no enrichment data could be fetched. Next, we can see this function in action by using an example IP address, 192.168.110. If the function successfully retrieves threat information, it prints the details, allowing analysts to make informed decisions on potential actions. If no data is found, a message will be displayed stating that no threat data was available. This automated enrichment process significantly saves time for analysts by streamlining the gathering of critical threat information. Now let's implement the following code to automate security checks in our Oz environment using Python's Boto 3 SDK. This script connects to the AWS EC2 service and retrieves information about the security groups configured within your account. By calling the describeSecurityGroups method, it obtains details about each security group, including their names and unique IDs. Next, we loop through the retrieved security groups to display their configurations. For each group, we print the group name and ID to provide a clear identification. The script then inspects the IP permissions of each group, which outlines the access rules associated with that group. For every rule, we print the protocols being used alongside the allowable port ranges, making it straightforward to evaluate what connections are permitted. This allows for an efficient overview of open ports and security configurations, which is crucial for identifying potential security vulnerabilities in your setup. Regular audits of these settings can help ensure that no unintended access points are left unprotected. Next, we will write a Python function called checkCompliance, which is designed to validate security group settings against compliance standards. This function takes a list of security groups as input and initializes an empty list to capture compliance issues. It iterates through each security group, examining its permissions. Specifically, it checks for rules that allow all protocols, represented by the protocol identifier -1. If such rules are found, it appends the corresponding security group ID to the compliance issues list. Once the function completes its checks, it returns any identified compliance issues. To operationalize this, we need to first call another function, listSecurityGroups, which retrieves the current security group settings from the AWS environment. After gathering this data, we pass it to our checkCompliance function. Finally, based on the result, we print either the list of compliance issues found or a confirmation message indicating that all security groups are compliant. This automation significantly eases the workload on security teams, ensuring continuous adherence to regulatory requirements. Now let's implement a simple Flask application that acts as a webhook to handle incoming alerts from a security system. The script begins by importing the necessary Flask class and the request object for processing incoming HTTP requests. We then create an instance of the Flask application, setting it up to listen for requests. Next, we define a route for our application with the @app_route decorator, which specifies that the /webhook endpoint will accept post requests. When a post request is made to this endpoint, the alert handler function is executed. Inside this function, we utilize request JSON to retrieve the JSON payload sent along with the request, which contains the details of the alert. The alert data is then printed to the console for visibility, allowing us to monitor incoming alerts. Finally, the function returns a confirmation message along with an HTTP status code of 200, indicating that the alert has been successfully processed. This setup not only facilitates the handling of alerts, but also lays the groundwork for more advanced workflows in a security orchestration, automation, and response (SOA) framework. Now let's take a look at how we can gather and analyze performance data to evaluate the effectiveness of our automated responses. We begin by importing the Pandas library, which is a powerful tool for data manipulation and analysis in Python. We then create a data frame containing sample performance data, where each row represents an automated action taken, either blocking an IP, notifying a user, or ignoring a potential threat, and the outcome of that action noted as either success or failure. Next, we calculate the success rate of these automated actions by utilizing the value counts method on the result column, normalizing it to obtain the proportion of successful outcomes. This gives us a clear metric to understand how well our automation is performing. The final step prints the automation success rate in a percentage format, making it easy to comprehend at a glance. This approach not only allows us to benchmark our automation's effectiveness, but also highlights areas for improvement, fostering a cycle of continuous enhancement in our security operations. In closing, we have ventured through the future trends of Python security automation, a fascinating intersection of programming, cybersecurity, and innovation. From machine learning integration and cloud automation to compliance checks and SOA enhancements, Python is well equipped to tackle the complexities of the evolving threat landscape. Automation will continue to play a pivotal role in enhancing security measures, streamlining processes, and allowing teams to respond with agility and confidence. As the environment evolves, so must our strategies, ensuring we stay ahead in securing our digital world. Thank you for joining me on this journey, and let's continue to explore these exciting trends in security automation together.